First thing, please use the microphone because we are in streaming and we need to let other people listen to what we are talking. So we will have to use either this microphone or this one. It's your choice. Even for the question, please ask for the microphone. Coffee break and lunches will be served in the court just outside here. So we will not need to move anywhere else. Tomorrow we will have a dinner and visit to Galileo House. The meeting point will be here at 5:30 p.m. So about 1 hour after the afternoon session will end. As I told before, there is a streaming. So if any one of you don't like to have you broadcast all around the web, please ask and we will shut off the camera for your presentation. And then welcome here. I will tell you something about the place here. Arcetri, the Florence Observatory was founded about the beginning of the 1900s, when Tuscany was still an independent state, and was in downtown. After about 1850, Florence was one of the first cities with public illumination, so it would become impossible to observe at night. And in 1872, the astronomical community obtained a new building on the hilltops here. This location was chosen because it was very near to last Galileo House, where the dialogue of the maximum systems were written and where Galileo spent the last years of his life in confinement. So it has a great historical value. In 1922, the observatory changed its name in Astrophysical Observatory, and because there was a great work in spectroscopy, and a solar tower was built. You can see it's still there, even if it is not operated since 1980, roughly. What we do here is, well, the place is very nice. If you want to have a walk during lunchtime, it's about, well, a few hundred meters, and you have a very beautiful landscape of the hills around. The place was named the Gioiello, from Galileo's time, and it is about as it was at the Galileo's time, still now. The Arcetri Observatory is part of INAF, the Italian institute that groups all the astronomical research in Italy. We have about 120 people working there, and most of them are scientists, about 60 staff people and 30 postdoc and other temporary positions. The main topics we study is still sun, that now is more related to plasma physics, coronal, chromospherical and coronal shocks. And there is also an instrumental work on large optical solar telescopes. We have historically we have been interested in comets. Now there is a new branch on astrobiology. In this building downstairs in the cellar there is a astrobiology lab where they try to reproduce the conditions in which organic molecules form. And we are involved also in space missions for astrobiology and in general for comet observations. You probably know everything about our solar star formation group, because it is much involved in millimeter astronomy. There is a group that studies cosmic rays, especially acceleration processes. And a extragalactic group that studies mainly the history of star formation in far galaxies, active galactic nuclei, and history of the metallicity and chemical evolution of the universe and cosmological times. We have a very large group that is involved in the optical instrumentation, particularly in the adaptive optics. We are partner in the larger binocular telescope. Is a twin 8-meter class telescope, for which we have built the secondary mirror, that is one of the most advanced adaptive optic system. This is a quite impressive image for the first light adaptive optic system, in which you can compare the space telescope image of a center of a globular cluster to the image we took with the high resolution with full diffraction limit 8-meter telescope in K-band. These technologies are useful for the new extremely large telescope. It is a 40-meter telescope that is being built by GISO, for which we are designing some adaptive optics, infrared, and spectroscopic cameras. The radio astronomy group is, well, I already told, is involved mainly in star-forming regions from Bok globus to protostellar disks. And also for, this is one image, maybe someone of you work actually on that. And also we are interested in studying with radio tracers for metallicity in far galaxies. The radio astronomy technology group is involved, has two main fields in which we have a very good competence, that is optics, electromagnetic optics. We are studying now way to reduce the size and the cost of electromagnetic optics components, for example, using 3D printer technology. And for digital signal processing, we contribute to the ALMA correlator. Is spectra like the one in which you have a 2 gigahertz of spectroscopy with 8,000 channels were possible because of a board developed here. Now we are involved in SKA. This absorbed most of what we do today. And we have a good competence in collaboration with Bologna for calibration techniques using drones that fly over the antennas, and for general digital signal processing for this very high resolution, very high number of antennas, etc. That's all. So hope you will enjoy it here. The stay. If you want to ask, are curious about any of these things, ask, and we will be happy to answer. And that's all. Welcome.
Yeah, thank you, Gianni. For this introduction into this very historic and very nice place here in Florence. And let me also welcome you in the name of RadioNet 3 to the last workshop we have in the Eratec, in the European Radio Astronomy Technical Networking activity in RadioNet 3, quite at the end of the program. Program stops with December 31. And I think this is one of the very last events in RadioNet, which has a slight, or which has a certain boundary condition, and I come back to that to you in the next days, because if you want to apply for money, you have to do it quickly. As I said, welcome again in the name of RadioNet, and thanks for the Italian colleagues for inviting us here. They did up to now, and I'm sure they will until the end, a great job presenting us this map, which represents a lot of work, doing all the preparations, the organization, and things like that. Let me point out some things. Of course, the important papers are these ones, not the other ones. But anyway, it's great. So you raised the level to a very high level. Okay. Yeah, that's more or less all for me to say for the welcome. We have a very tight program. It's from my point of view, what we organized in Eratec. It's one of the very big workshops. A lot of talks. We have a tight schedule, so please, to all the speakers, keep in time, restrict yourselves, and don't make the chairman's a too hard a job. So thank you for that, and with this, I think we can start with the first paper.
Hello, my name is Taehyun Jung from K. And the first session is millimeter wave analysis method, which is invited talk from Maria Rioza about the analysis method for millimeter wave using multi-frequency observation. So I would like to give 30 minutes talk to invited speakers, and the other speakers are 20 minutes talk and 5 minutes question. So I'll give you a sign when 5 minutes before.
Sorry, just one question. There are the parking that are where they are not allowed for parking. They are a Clio and Mariva. So maybe someone of you have such a car, rent cars, no? Is red a Clio?
And
Meriva.
Great one.
Okay, so probably la tua. Okay, thank you. Sorry about that.
Okay. Hello, good morning, everybody. It's really a honor and a pleasure to be here. And so my talk is the first one of the workshop to warm us up a little bit. I hope I managed to raise you the interest in this. So the title of my talk is Methods for Millimeter VLBI Using Multi-Frequency Observations. In a summary, it talks about the power of multi-frequency observations to improve the performance of millimeter VLBI. Yes, so first an overview of my talk. I will talk about what are the issues around millimeter VLBI. And then I will present a method, a description that we call source frequency phase referencing, and what it achieves is an effective atmospheric compensation, and by doing that it enables an increased coherence time, that's an increased sensitivity, and also astrometry at the very high frequencies. Then I will present an empirical demonstration of this method using observations with the Korean BLBI network up to 132 gigahertz, and then I will do some last overlay of a work in progress, and basically also linking this talk to the next one coming in these 2 days. So this is the BLBI world with a number of networks, well-established networks, and certainly the BLBI observations at centimeter wavelengths is a very well-established field. They have technological developments, advanced analysis techniques, achieves micro-Jansky sensitivities, micro-arc seconds, astrometry. So this really results in a widespread application. So it's applied to a wide variety of targets to many fields of study. In observations at higher than 43 gigahertz, there is the BLBI observes up to 86 gigahertz, the GMVA, and more recently, it came to operations the dedicated millimeter BLBI array, the Korean BLBI network, with an innovative system of having simultaneous observations at 4 bands. In comparison with centimeter BLBI, certainly the millimeter BLBI is not so widespread. And okay, thanks. The reason is that it's not interesting. It certainly is very interesting. To start with, one achieves the highest angular resolutions. Going to higher frequencies, there is a unique science to be addressed with it, and also with the ALMA era is really an exciting field. The problem is that BLBI becomes progressively more challenging when the wavelength gets shorter. So there is a very limited sensitivity that comes from the limited aperture efficiency of the dishes. The receiver system temperatures are high. There is a fundamental limitation coming from the rapid phase changes imposed by the tropospheric propagation, and which is linearly proportional to the observing frequency. And the effect is that the time over which the signal can be coherently increased is reduced as going to the higher frequency. And then it doesn't help it that the sources are in generally intrinsically weaker. So the result is that this has a limited application to a handful of strong sources. And for example, this is the formula for what is the minimum source flux detected, and in order to decrease this number, one can go and make a smaller system equivalent flux density, for example, through having a huge, massive collecting area. So that's why the phase ALMA is a really very exciting element to have a good detections in a very short coherence time of the troposphere. And also, it is possible to increase the coherence time. And this talk is about this, the power of using multi-frequency observations to compensate for the tropospheric fluctuations and hence increase the sensitivity of the array. And of course, both combined would be even better. So starting with centimeter BLBI, phase referencing was certainly a game changer. It improved the performance with improved sensitivity, improved precision, and the way that this works, it does it, is by interleaving observations of a nearby reference source to correct for these errors among them the tropospheric, and then it allows the coherently add of the signal in the target source well beyond the tropospheric coherence time. Because the two sources are not observed simultaneously and because they are not along the same line of sight, this requires temporal and spatial interpolations. And also, very important for this to work, the telescope switching time, it has to fully sample the tropospheric changes. So for example, at 22 gigahertz, one would do, this is what the telescope follows, alternate between the target and the reference at a certain rhythm. 1 minute, maybe, can go to higher frequencies. Oh, sorry. and this achieves higher sensitivity and astrometry. One can go to higher frequencies if one moves the telescope faster, because to sample these tropospheric changes. So it would do like this. And then, obviously, there is a limit of how fast the telescope can move, and this sets the limit of the application of phase referencing, which is, in general, 43 gigahertz. Okay? And this also limits, it sets where the limitation of the performance of VLBI starts, where phase referencing cannot be applied. So, an alternating approach, I've been calling this trans-source because uses one source and transfer it to the other, is to use a trans-frequency calibration. So it would be using alternate between the two frequencies and use the low frequency, which I use here the color code red, to calibrate the high frequency, which I use the green. I will use the color throughout my presentation, this color code. So this at heart is quite similar to phase referencing, where the roles of the two frequencies and the two sources, they are interexchanged. So in phase referencing, the troposphere is similar at the position of the target and at the position of the reference. In this one, the ratio between the tropospheres is given by the frequency ratio, because the tropospheric fluctuations are proportional to the observing frequency. And so of course, the first observations of these ones were done with the BLVA using a fast frequency switching. Fast frequency switching for a telescope with frequency agility is an easier operation than source switching. So for example, the BLVA can change, it takes 10 seconds to change between frequencies. Because of that, one can go to higher frequencies. So with this, one can go already up to 86 gigahertz. It just works with this 10 seconds time, but it goes beyond what the phase referencing does. And of course, and if one wants to do it better, what one would do is what the KVN does, which is an engineer in developing, addressing this issue, and it's having, instead of alternating very fast, you have simultaneous observations at two frequencies. By doing that, there is no need of making any interpolation, and then the compensation of the tropospheric fluctuations is as good as it can get, and this means that one can go to even higher frequencies. So this is the picture of what the KVN does with these multi-channel KVN receivers, and this is how the four receivers, they can observe simultaneously, 22, 44, 83, 132. By doing that, one can increase the sensitivity by enlarging the coherence time, but one cannot get astrometry. And this is a brief description of how this works. We call this method frequency phase transfer. So one has this is the typical nomenclature of the residuals, phase residuals coming out of the correlator at the two frequencies, red for the low frequency, green for the high frequency, residuals coming from the errors in the a priori models for the geometry, troposphere, ionosphere, instrumental, structure, inherent 2P ambiguity. And here I put the changes, the temporal changes of these variations. These residuals, they have a different temporal structure. Some change very fast, like the troposphere. Others, they are slower. The way to do this analysis, one, do the analysis of the low frequency using self-calibration normally, scales up by the frequency ratio given by R, and uses these solutions, this calibration, to blindly calibrate the higher frequency. By doing that, the geometric and the tropospheric residuals being non-dispersive, they are directly, completely cancelled, and other remains. The dispersive ones, the ones that depend on frequency, and even they can get even larger. This is the case of the ionosphere. But the important thing is that the fast variations, they are compensated, because by doing that, we have compensated the troposphere and we have extended the coherence time, so we can integrate longer. So we can have an increased detection, increased sensitivity at the high frequencies, and because we have all these terms which are remaining, the dispersive, we don't have astrometry. To do astrometry, a second step is required to remove all these remaining dispersive terms. So this can be achieved, for example, by including the observations of another source, a second source. So both sources are observed following this same scheme, simultaneous observations at two sources. The observations are alternated, as you see them here, one source, another, and then one analyzes the two observations in the same way with the frequency phase transfer and uses one to calibrate the other. This is exactly in the same fashion that phase referencing works. Use the analysis of one source to calibrate the other. Now, because what we want to compensate for are variations that they have a slow change, we really don't need to move the telescope fast, because the changing of the telescopes, it will match these variations. So it can have a very slow source switching, put here of several minutes. And by doing that, we get rid of the common things, which would be all of this ionosphere, instrumental, and really this two-step calibration procedure, it retains the astrometric information that comes from a position shift of the frequency between the two frequencies of the source. Okay, so by doing that, we have isolated the astrometric information and we can have astrometry. So with this two-step calibration, we do have increased coherence time and we do have high precision astrometry, and all of this at very high frequencies, the highest frequencies that can be achieved nowadays. So because the slow antenna switching is okay, the antennas don't need to move very fast, and because the source separation can be also very large, I will come back to that a bit later, it's really very applicable to many sources and many fields. Okay, so all of this is very good in paper, so we set ourselves to make a demonstration to see if it would work with real observations. So for that, we carried out observations with the Korean VLBI network, which is this dedicated millimeter VLBI array up to the highest frequency, 132. And these observations were carried out in March last year. And so we selected a number of these 5 sources because they had detections at 86 gigahertz. They had never been detected at 132 gigahertz. Not detected, had not been observed. And then we have selected a handful of them, and we also wanted to test this thing, how far the sources can be to see in this method. So we selected a range of separations between 3 to 11. So there were some closer, some very far away. And then the schedule consisted of 3 minutes scan long on each source, and alternating between the sources within one triangle, and then we alternated between triangles every 1 hour and a half. So we were in this triangle, 3 minutes in each source, 1 hour and a half, and then moved to the other, 1 hour and a half. Although I will not go into detail in that, we selected these multiple sources so that we could decompose the relative frequency-dependent positions into individual sources. But I will not go into that. But there is a reason why we chose all these triangles and different. So also for just curiosity, this is how the maps look like in a high resolution at a lower frequency. So you also see. So, okay, so we made the observations, we recorded at the 4 frequencies simultaneously, alternating between the sources, and we did that for 8 hours. And then we started the analysis. So I'm going to talk about the 3 aspects. One is the effective tropospheric compensation, and then I will talk about the astrometry, and then about the increased coherence time. So this is the first one. So this is how the raw phase is coming out of the correlator at 22 and 44 gigahertz. So one can see, so this is 8 hours, so each tick is 1 hour. One can see how the phases, they vary very fast, and they vary increasingly faster at higher frequencies. This is like the signature of the troposphere, it does that. So when you put yourself to integrate the signals, you really have very little time before it changes 1 radian. So your source has to be very strong. So using this trans-frequency calibration, we take the observations, this one, analyzing within self-calibration, multiply times 2, this is the frequency ratio between 22 and 44, and applying it blindly to this data. So this data then becomes this one. So as you see, there is a really remarkable compensation of the fast fluctuations. The degree of coherence has remarkable increased, and this is for a one source, and this is when I superimpose all the sources. So this is doing this triangle, one triangle, another. So this is this is the data at 44 gigahertz calibrated blindly using the data from a lower frequency. So this is until here phase referencing can do. Phase referencing can do astrometry at 43 gigahertz and increase coherence. So we continue higher. So this would be the data coming out of the correlator at 88 gigahertz, even faster variations. And then I use the same, using the 22 gigahertz as the low frequency to calibrate this one. I take this, analyze self-calibration, multiply times 4, now is the frequency ratio, and apply to this data. And this data becomes this. Okay, so again, degree of coherence, one can follow here the phases for longer periods, much higher than that. This is for one source, this is for all the sources. You see how the residuals also, they come increasingly larger when the frequency ratio goes, yes? Okay, so this is 8 hours, 8 hours. So each of these ticks is 1 hour. And for the highest frequency, the 132 gigahertz again. So this is the fastest, and again, using the 22 to calibrate this one, now the frequency ratio is 6. And this is what one gets for all the sources. So clearly it is the rate of change varies, but here still one can follow very well all the way through when you could not follow them here. So this means that you could integrate. And it's also remarkable to see how the agreement between the variations of all the sources. So all the sources are dominated by something common to all of them. So this was using the low frequency 22 gigahertz for the calibration. This is now using the 44 gigahertz. It results in something like that. So this is 44 to calibrate the 88. The ratio is 2. You see again, the 88 comes beautifully aligned. One can really integrate here for long periods of time. And this is 44 to 132, a factor of 3. This is how it comes. For comparison, you can see the gain of using 44 to calibrate 32 compared to 22 to calibrate 132, where here the ratio R is larger, and then the residuals are also very faster than this. So it is good to have a short frequency ratio to slow down the phases. And this is to remind you the analysis from before. When we make this frequency phase transfer, this transfrequency analysis, we have these remaining phases, remaining errors. And these ones are what we see here. And they are slow, which increase the coherence time, but they also means that there is no astrometry. These remaining aspects, these remaining factors, it means that there is no astrometry. So in order to get astrometry, as I said before, we want to interleave the observations of a second source that will help to compensate for this remaining. So I'm going to present you two cases or two source pairs. I've chosen really the more challenging one. So that's the frequency at 132 gigahertz and the second weakest source. So this source do not have direct detection 132 gigahertz. And the separation is 6 degrees away. So this is just what we saw until now, the transfrequency calibration for a one source, 4332, and the transfrequency calibration for the other, 2007. So I use, as we have been seeing before, the agreement between the two sources is pretty good. They follow each other. So one can use one to remove all these trends from the other. By doing that, this is what one gets. So this is this data calibrated with this. So now we see that the phases are much more flatter. All these residuals, they have been compensated with size and even longer increasing coherence time. But most importantly, now we do have an astrometry. So by making the Fourier transform of this data, one gets a source frequency phase reference map, completely equivalent to a phase reference map. So the offset of the peak of brightness with respect to the center of the map is convey the astrometry information, which is the position shift between the two frequencies. So one has this type of information, and one can assess how good this calibration work. So this is this quantity, the flux recovery, percentage of the flux recovery, which tells you the ratio between the peak of this map and a peak if you would have a perfect self-calibration information. So these values are very large. It means that the incidence of errors in all this calibration is really very small. It means that the propagation median has been calibrated pretty well. So a large flux recovery is a meaning of a good calibration strategy. I will come later to this flux recovery quantity. So this is now an astrometry map at 130 gigahertz. So this is the first map that exists at astrometry at 130 gigahertz. So as I said, there is no detection at this source, and the astrometric errors also, they are incredible. They are 30 microarc seconds. This is with a baseline 400 kilometers length of the KVN, relatively short. These errors will scale proportional to the baseline length. So a baseline length 10 times longer would mean this error 10 times smaller. And this is a second case of now I've chosen to represent two sources that are very far away, since we wanted to try how far the sources can be. So these are, again, this is the weakest source of all, non-detected at 132, and 11 degrees away. So this is one source, the other source, and same story. Good agreement between both as expected from the dual calibration. Use one to calibrate the other. All the residuals disappear, the faces turn much more flatter, and more importantly, they retain the astrometry information. So this is again the map, and one can measure the astrometry, and we have an 87% flux recovery, indicating the incidence of errors is really small, so they have been removed by this calibration. And so again, an error 50 microarc seconds like before. So this really implies the wide applicability, because one can go very far to find a second source that could be used for this analysis. Up to 11 degrees, we could make it work. So all of these results, we have done that for all the source pairs, for all the frequency pairs, and this type of values, this astrometry thing, we have represented it. So remember how this looks like? Using a polar plot, which are like that. So this is one of these arrows here. So the colors are for the different frequency pairs, and all of these are for the source pairs, one of them. This is just a curiosity to show you how it is. From here, one can go and decompose the position shift at each source for between all the frequency pairs, and one would get things like that, okay? I'm not going into more detail about that, but this is really the outcome, the important outcome for the astrophysical applications, because then we measure the absolute position shift for the image registration of the images. Those are really these numbers. So this would be applied for any spectral studies, and AGNs for spectral index, rotation measure map, core sheets would tell you how much you have to shift the map of the AGN at one frequency and at another, so you can impose it. Also for measure transitions and evolve star-forming regions to align the spatial distribution. So this is the kind of thing, the end of the astrometric analysis for all these applications that we will be hearing in the coming sessions. Okay, and finally, the other thing very important from this compensation of the tropospheric fluctuations, of course, is the increased coherence time, because this is directly means the increase of the sensitivity and how weak sources can be observed. For that, we have again selected a challenging data set. So this is the weakest source, and the data 130 gigahertz, and it is calibrated with the 11 degrees away. And we have made a pre-analysis with this dual frequency, the frequency phase transfer, that has these residuals left, and the source frequency phase referencing that have much flatter. So we have made this pre-calibration, and then we've done the normal self-calibration and look at the maps that come, and use the value of the peak flux recovery that I was mentioning before versus the phase solution interval time. And as one would expect, the peak flux recovery, it decreases with phase solution interval times because you are sampling less often, let's say, the solutions. So the coherence time is defined as the solution interval for which the peak flux recovery is a 60% fall. This corresponds to an RMS phase errors of 1 radian. So for the FPT calibration, it is about 20 minutes we can integrate before we lose the 1 radian. For the source frequency phase referencing, we certainly haven't found a limit. We integrated for the 8 hours with a mere 20% decrease in the flux. So this means that the effective coherence times we've got is 20 minutes and 8 hours. And one has to remember that the typical atmospheric coherence time at 130 is about tens of seconds. That would mean that one can increase all this integration time. So certainly we do not know of a higher limit where this method can be applied. And in this context, there are a type of man-to-man mode observations or tests going on in ALMA, where they are applied at 650 gigahertz. So yeah, that's just to going back to the beginning to my talk, how an effective tropospheric compensation is directly maps into the increased sensitivity of the array. Okay, and just to summarize what I've presented, I try to pass the relevance of the multi-frequency observations to improve the performance of millimeter VLBI. With this method, which we call source frequency phase referencing, one achieves a really superior compensation of the tropospheric fluctuations that leads to very high precision astrometry, to increase sensitivity, boost the array sensitivity. We don't know of an upper limit. We really think that it would continue to work to much higher frequencies. It's widely applicable because you can have a second source very far away. You can slew between the sources very slowly. It makes a very effective use of the time because you have also this data set at many frequencies. And there is technology ready, really the KVN has it ready. I've presented the empirical demonstration with observations up to 132 gigahertz, the first time astrometric measurements at 130 gigahertz, and the test, empirical also demonstration, the coherence time extended up to 20 minutes and 8 hours. And I've mentioned why are they important astrophysical applications. And my last slide is to put this in context with the coming talks. So there is, of course, a lot of things going on in the frame of this source frequency phase referencing KVN. So one of them is the network. There is, of course, having a longer baselines is very important to increase the resolution, the astrometric precision. So as part of the KVN pilot project, there is already observations with the international baseline KVN to Australia and to other places. So we will hear about that tomorrow morning. Engineering, there is, other than the current KVN, there are possibilities for near simultaneous multi-frequency observations. We will hear also tomorrow. From the analysis also, there are many news going on. We are working on something called the ice blocks, which consist of including in the analysis parts where we observe at the low frequencies and measure low frequencies being 1.6 gigahertz and measure the curvature of the delay at these low frequencies to estimate the ionosphere, the Eratec. And this would replace, in a way, the role of the second source to calibrate the ionosphere. So in that way, you have only one source. This also will be presented today in the next session. And of course, the unique science drivers that we will hear today, both for a continuum, for a lines, evolved star formation, in general weak sources, and many KVN applications. I focus myself here in continuum, but there are also KVN applications to the spectral lines that we will hear also about today. Okay, that's it. Thank you.
Just a comment more than a question. Your frequency ratio between the lowest and the highest is 6, which is very much the same, by chance, than what the geodesists have in VGOS. They have a range from 2.3 to 14 gigahertz. And they have been implementing fringe fitting over the whole frequency range in one go, and at the same time estimating a dispersive delay. And I would suggest to study this for your case, where I would think this is also a method to determine your dispersive delay, the remains of the whatever is left up there of the ionosphere. You don't have a phase scale as they have, but there's also something called manual phase scale, and that could help most projects which are not so much interested in determining a precise separation to a nearby source, but just for registering the different aspects of the source at different frequencies. Of course, it's complicated because you may have to take into account source structure usually. Geodesists try to avoid that by using just point sources, but I think it's something worth studying.
Yes, I think it's where's this yes. Yeah, definitely it sounds very, very interesting. It sounds along the line of what we are trying to do that Sol will present, and we definitely should look into that. Yes, thank you.
Just a small comment with regard to the limited number of sources available for millimeter VLBI. This is no more true. I mean, at the moment we are limited to 2 gigabit per second bandwidth for the VLBA. But the EHT, which goes to 230 gigahertz, has already observed at 8 gigabits per second and will soon go to 32 gigabits per second. So the aim is to use 4 gigahertz instantaneous bandwidths for all observatories, and that of course means that switching between sources is no more so much limited by the slew of the telescopes, because if you spend 1 or 2 seconds on the source, then it's enough. So we are going to much higher bandwidths, and that comes basically from the incorporation of ALMA into the VLBI. So I think for the next very future, all observatories should consider going to 4 gigahertz bandwidths at any frequency, and that will relax some of the sensitivity problems quite dramatically.
Yes, certainly. Increasing the bandwidth is a way to boost the sensitivity as well. But with respect to phase referencing, you need to have a source very close. It's not only that would be detected, so I don't think it's going really to have a wide application, phase referencing to the very high frequencies.
Yeah, first, I'll just respond to that one point. 4 gigabits per second will give you a factor of 4 in bandwidth, say, or a factor of 2 in sensitivity. This gives you a factor of 60, because you've gone from tens of seconds to 20s of minutes. So that's even so. You're looking at you've got to get a 60-fold increase, and you're not going to get that out of bandwidth.
Yeah, so I just wanted to ask, or to try and get a feel of what flux density you do actually need for calibration sources, say at 100 gigahertz, because we've been doing searches for calibration sources. I mean, for ALMA, we can now use 40 millijansky sources. But, I mean, I guess probably, even if you're talking about, say, half a Jansky, then I think what you would be able to pick targets that had suitable phase reference sources within 1 degree. There are actually more sources than we thought that are bright enough. But I think it would be a matter of choosing your target according to the availability of phase referencing. But I mean, I'm just plucking numbers out of the air because I don't know what you need for the other, VLBI without ALMA or a long way from ALMA.
So, well, what you really need is to detect direct detection of the sources at the low frequency. Yeah. So, if you go lower frequency, it will be easier because the detection limit is higher.
May I give us some comments on that? Actually, according to my experience about the frequency phase transfer using the KVN, actually KVN baseline sensitivity is about 0.5 millijansky at 2 minutes or 3 minutes with the integration. And then in my experience, more than SNR, more than 20 gives a good, to transfer successful phase calibration at higher frequency from 20 to 30, 130 gigahertz. So I guess But actually, the actual situation is more harder than more than 40 millijansky. Or anyway, SNR is quite important to removing the delay errors. So it's around
what
the
do you
50
think is,
millijansky, something like
20
that.
millijanskys, for example, at the low
Yeah,
frequency.
but actually, yeah, but more than that, maybe 40 millijansky, same as yours. Yeah.
Yes, because you can go also very far away, really. Yeah.
Maria, I'm curious about what are the sources of errors that prevent you from getting large coherence time using the frequency phase transfer? Because with frequency phase transfer, you said you get something like about 20 minutes of integration time, but when you use an external source, then you increase that to 8 hours. So clearly, there are some errors that you have not fully calibrated with this, frequency phase transfers. Do you have an idea what are those terms, tropospheric, ionospheric, or
So
instrumental?
there should be the dispersive terms. Everything non-dispersive would have been calibrated with the FTP. Dispersive terms, they are the ionosphere and the instrumental. I think what we see here in the KVM, I think there is a large instrumental contribution that with a system in place to calibrate with the KVM people are working on, it will not be so much. So I think it's dominated by instrumental terms, what we see there.
Connected on that, if you get for much longer baselines, the ionosphere will be much worse, probably because over Korea, probably you have some common values, but if you go,
Yes.
cross the ocean,
Yeah,
it's much worse,
it
no?
can be. We also need to, we're working on that on the long, so on the long baselines is one of the things to try. If this coherence that we see here, they continue to be the case on international baselines. Yeah.
Okay.
Yes.
So you showed us the frequency corrected phase residuals at different frequencies, and it seemed to get faster as you go to higher frequency. But this is the residual, this is the non-dispersive part, right?
Mm-hmm.
So that's clearly not ionosphere because it gets worse with frequency, with high frequency.
But also you boost the ionosphere at the low frequency by a factor larger than the frequency ratio. So you are thinking you are doing things very bad by having a large R, a large frequency ratio.
I have another question, if I can. You showed this.
Sorry, and it is not ionosphere. We have been comparing the residuals at the different frequencies, and it has to be something else. So we think that with the KVM, the instrumental contributions are the dominant.
Yes. So when you do source frequency phase referencing, use a reference source to calibrate the dispersive terms. So as I understand it, you have to be able to detect, independently of referencing, you have to be able to detect the reference source at both frequencies and the target source at the lower frequency in order to be able to do the correction to detect the target source at the higher frequency. Is that right?
No, only you need to detect both sources at the low frequency.
Okay.
Because at the high frequency you have the extra coherence time coming from the dual frequency calibration. So also at the reference, you will have the increased time from the low frequency.
Okay.
Thank you. May I move to next session? Let's thanks to the speaker. From Asian Jet.
this coherence time at millimeter wavelength, and this is something that we really need for getting the most out of the millimeter VLBI observations. If you perform simultaneous millimeter VLBI observations, then there are many two ways of using this for the study of AD and jets. These are the two main topics I'm going to discuss. One is the use of the opacity curve shift, which can provide a lot of information about the jet formation, scale, range, strength of the magnetic field, and other parameters. And perhaps the most useful one is the Faraday rotation analysis. You are able to determine the rotation measure in these sources. You can get the three-dimensional structure of the magnetic field, which is really one of the most important parameters to understand how jets are coordinated and accelerated and so on. And also jet mass content, acceleration rate, and so on, as we will see later on. Of course, you need to compare these images at different frequencies, and it's really very important that you have a very good image alignment across the different frequencies. This is something that it has been shown lately that it may really affect significantly your results if you don't get a proper image alignment. This has been done usually just by matching optically thin components in the jet, and lately by using two-dimensional cross-correlation analysis. Here it is also where Maria and Richard's technique about using source frequency phase resonance can give you really the astrometric precision that you need for the comparison of these images together with boost in sensitivity. As you know, it is shown in this animation made by Wolf and Stefan, AD jets are launched by the creation of materia onto supermassive black holes, but the actual mechanism for jet formation is really still largely unknown. Helical magnetic fields are the key. They are supposed to be anchored either on the black hole or in the accretion disk, and they are supposed to be playing a major important role in jet formation. So this is what we really want to study. I'd like also to mention that nowadays we have now an amazing tool for the study of jet formation. We have this general relativity image dissimulation, which are becoming absolutely amazing. 10 years ago, they were not able to get any jet. They would be able to get a noise factor 1, 2. Now easily, all these codes can get a noise factor of beyond 10. And this is an example of mechanical simulations that you can obtain. You can combine the general relativity MHD with some emission models, ray tracing, and study the jet opacity, depending on the behaving angle, and so on, and get a lot of constraining of the parameters for jet formation. Jet formation is expected to take place within the innermost 5 to 20 expansion radius from the central black hole. And for the most massive and closest sources, like M87 and Sagittarius star, this requires an angular resolution of the order of tens of microseconds. We are getting really close to this. So we can achieve that with either ground-based millimeter VLBI observations, such as the GMBA or the Event Horizon Telescope. I'm not going to talk in detail about this because I believe Thomas is going to cover the topic in more detail later on. But we can also use space VLBI for getting a very high angular resolution. And we can combine both. And this is just an example of the kind of studies we can perform. These are two images of BLAC. This one is obtained with radiostron at centimeter wavelengths. And this is with the GMBA 3 millimeter. You see we are reaching very similar angular resolutions at different wavelengths, probing similar jet structures in the jet. So this is really a very powerful tool for the comparison of centimeter space VLBI and ground-based millimeter VLBI for the potential study of Faraday rotation, opacity, color shifts, and so on at the matched angular resolution. I'm going to talk later on a little bit more about that. So let me now move to how one of the two big methods, which is the use of the opacity curve shifts. As you know, the VLBI core is defined as the jet location at which the jet becomes optically thin from the optically thick regime. So you have a transition between thick and thin, which it is also coincident with the peak in total intensity. The position of the VLBI core depends on the observing frequency, and this is very straightforward to understand. This is just particular, Kazuhiro Hara and collaborators have used phase reference quasi-simultaneous from 2.3 to up to 7 millimeter VLDL observations of M87 with respect to M84 to determine what is the jet collimation scale length. The method is based on the Blanford and conical jet model under the assumption that the jet is conical and the central black hole sits at the home apex. These are Hada and collaborator observations we have here in M87. This is a zoom into M87, and you have marked here the positions of the VLBI core up to progressively higher observing frequencies. And they fit this core separation as a function of frequency. And they obtain this very nice fit with the observing frequency to the power of -1. And this is actually what you would expect from the Blanford and conical jet model, and assuming also probably equipartition of energy between the particles in the magnetic field. So really an amazing observation, especially because this was the first time that it was taken all the way up to 43 gigahertz. So if you compare now the position of the core at 43 gigahertz with the asymptotic core position, then you get an estimation of what is the position of the VLBI core at 43 gigahertz with respect to the black hole. And they got 41 microarc seconds. And this is about 6 spatial radii in projection. If you the projected is about 10 to 20, spatial radii. So if you assume that the black hole really sits here, and we will come to that later on, then Kazuhiro Hara et al. Obtained that the jet formation scale length in M87 is of the order of tens of spatial radii. Truly amazing, nice physics work. Now, this differs significantly, really, about that from the observation taken for blazar jet. There has been a number of studies, mainly using timing of multi-wavelength flares in different sources. And I'm listing here some sources from different authors. And all these observations imply that you have like a dip in X-rays and then a flare in radio. And they timing, if you time these flares at different energy range, you get an estimation what is the distance between the VLBI core at 43 gigahertz and the central black hole. And all these observations suggest that is of the order 10 to the 4, 10 to the 6 spatial radii. So we are talking about 4 to 5 orders of magnitude difference with respect to Kazuhiro Hara observations of M87. Let me give you a flavor of these kind of observations, and this corresponds to my student Carolina Casalio's work on CPA 102. You have here the light curves. This is gamma rays. This is a huge outburst of gamma rays, the largest observed. This is X-rays. This is ultraviolet. This is optical, and then all the way to millimeter. You see, there is a huge outburst almost at the same time at all the observed wavelengths. If you compare this with the VLBI jet, and this corresponds to 7 millimeter VLB observations from the VLB blazar monitoring, you see that this huge flare is coincident with the passing of a new superluminant component through the core. So how do you explain this with the core being an optically thick thin transition? That's extremely difficult because the passing of a superluminant component through this optically thick thin transition won't give you at all the energy burst in particle acceleration, particle energy density that you need to produce these huge gamma ray flares. So a possibility that we are considering is that the VLBI core at millimeter wavelength may correspond to a recollimation shock. The interaction of a moving shock and a standing shock does produce a huge particle acceleration that could give you the high energy multi-wavelength flare. And just to give you an idea of the physics that support this, these are the relativistic MHD simulations we have performed. And as soon as you have a pressure mismatch between the jet and the solar medium, you would easily get a recollimation observed. This has been extensively studied by different authors and so on, so it's very easy to get this recollimation shock. You do expect to have that. You see many standing features when you move deeper into the inner part of the jet. the emission at different frequencies, and you mark the position of the peak of the VLBI core, then this is what you get. And at centimeter wavelengths, we do get the expected core opacity core shift. So there is no contradiction with all the observations of core shifts at centimeter wavelengths. But when you move to millimeter wavelength, especially 43 to 86, you don't see the optically 16 transition. You start to see the recolocation shock. And this is a physical position in the jet. It's a physical thing. It's not just depending on certain frequency. This is a location which in the jet which corresponds to this recolocation shock. And that would break down this nice feed of the core position with frequency. And we do require this for the explanation of the multi-wavelength observation. So our theory, our model, working model now is that at centimeter wavelengths, this corresponds to optically 16, but a millimeter, we should be able to see the VLBI core as a collimation shock. And this is something we are testing now with a sample of sources being observed with the VLBI at different frequencies using some astrometric precision measurement together with Maria Reoja and Richard Dawson, and Sol Molina, my former student, is going to talk in her talk next about this. So now let me move to how we can determine the magnetic field strength from these opacity core shifts. So for a conical jet, conservation of particle number, magnetic flux, and adiabatic expansion can give you what is the evolution of the magnetic field and electron density number along the jet. You define the core position, in this case just as the core optically thin transition, that you have the position of the core of the optically thin transition, which depends on this parameter Kr, which in turn depends on how the magnetic field and particle number density decays along the jet. For a departition, this is about 1, and then you get that the position of the VLBI core depends with frequency to the power of -1, which is had a observation in other observations. This depends on the gamma parameter, which is just a measure of what is the core shift, at 2 different frequencies. So once you have this measure, you can get an estimation of what is the magnetic field at a given distance from the central engine, say 1 parsec, and it's given by the core shift, and also Doppler opening angle and viewing angle. And from this, you can determine what is the magnetic field at the core at different frequencies. So in principle, easy to do. This has been done by many different authors, and this is just an example of the kind of studies being performed by, this correspond to O'Sullivan and Kapusta, from the multi-frequency VLB observations of 6 blazars. This is, for instance, VLAC at a spectral index between 15.2 and 1.3 and 7 millimeter. And again, you have a nice feed of the core separation with frequency to the power of approximately -1. From this, they have been able to determine the magnetic field at about 1 parsec, which is about 0.14 Gauss. Reasonable number. So you take some assumption for the luminosity, and then you come to typical values of 10 to the 3, 10 to the 4 Gauss for the magnetic field at the position at which jets are formed. So a very powerful tool for getting an idea of the magnetic field strength. Now let me move to the other very important kind of studies you can perform for the study in ATM jets. And this is Faraday rotation analysis. This is indeed one of the most powerful tools. As you know, Faraday rotation produces a rotation of the observed polarization. This will be the observed one. This will be the intrinsic. And the rotation depends on the square of the observing wavelength and the rotation measure. And the rotation measure, given by this equation, depends mainly on the electron energy density. And this is the important part. And this is the scalar product, which means that this is the component of the magnetic field that is aligned to the observer. So, say you have now millimeter VLB observations with improved coherence time, and you are able to get the nice here, this is the rotation measure map, and if you plot across the jet width, they were able to obtain this nice grading in rotation measurement, meaning that the magnetic field component in the direction of the server changes across the jet width. Very important information. Perhaps the most comprehensive studies of other rotation in AGN jets was performed by Taniki Hobata from of the Mojave dataset, Mojave sample. They were observing 149 sources from the Mojave, and they did that with the VLBI at 4 frequencies between 8 and 15 GHz. This is a really an amazing piece of work. A lot of work and really nicely, very precise work. And out of all, sorry.
Okay, and they in this out of this number of sources, they observed rotation measurement gradients in 4 sources. CTA 102, as shown here, this is the gradient. 4C39.3.25, which is a special source because this is not actually the core. And other sources like 3C273. And here, you see again, this is like a textbook case. You see very clearly rotation measurement gradients across the jet width at different jet locations. And furthermore, they have been able also to observe a variation in the Faraday rotation screen with a period of about 3 months. And they are claiming that this is indeed difficult to explain by a sheath surrounding the jet, because you don't expect to have a variation in the Faraday rotation screen in just a 3 month period of time. So they are claiming that perhaps there is some intrinsic Faraday rotation going on in 3C273. For 3C454.3, they obtain these images, some gradients, and also a very striking structure in rotation measurement. If you look at this, you notice that there is like a symmetry of the rotation around the jet. It's like it's changing with position angle with respect to the core. This has been further studied by Samanina Saab and collaborators, and they have also performed a 2-dimensional histograms of the rotation measurement, the total intensity, the degree of polarization, and the polarization angle. And they have been able to successfully model these variations by, this is the model, as you see, by assuming that the jet in 3C454.3 is threaded by the larger scale helical magnetic field, which would explain this point symmetric structure around the core. As I said before, we can use also space VLBI for the study of Faraday rotations. And as you know, space VLBI, as I said before, provides an increase in angular sensitivity, so you can compare this with ground-based millimeter VLBI at much angular resolutions. The first polarimetric space VLBI observations, obtained also at 22 GHz, were performed on November 2013. We observed VLAC with the radioastronaut space mission together with an array of ground antennas. And this is the UV coverage we obtain. As you see, these are the ground-based baselines, and these are the ground space baselines. And in this plot here, we have the fringe-fitted visibilities, amplitude and phase. And you see that we were able to successfully recover fringe detections up to about 8 Earth diameters in projection. With this, we were also able to determine what is the intrinsic, that is the boosted brightness temperature and exceeding about 3 times 10 to the 12 Kelvin, which suggests also departure from the equipartition for BLAC. And these are the images we obtain. These are with different weighting schemes. These correspond to natural weighting, and you see here total intensity in contours. Colors indicate the linearly polarized emission, and white bars, I hope you can see them, are the electric vector position angle, so the polarization angle. And you see the core of a BLAC and then the jet extending to the south, and with an angular resolution of about 0.1 microseconds. Uniform weighting gives you an angular resolution of about 30 microseconds. You see also the jet and the bent structure in the innermost part of the jet. And if you use super uniform, then you get still we were able to successfully recover polarized flux, and we are reaching an angular resolution of about 20 microarcseconds. This is just being submitted to APJ, and we believe that this is probably one of the highest angular resolutions obtained today, showing also polarization in the jet. So we combine this with the millimeter ground array observations, and we obtained the Faraday rotation, the rotation measure image that is shown here. Again, now contours show total intensity, and colors in this case indicate the rotation measure. If you concentrate on the core area, and if you plot the similar two-dimensional histograms, and which is just the values of the rotation measurement and EVPAs as a function of position angle with respect to the core, you get this nice variation, nice systematic variation. So you do have these variations in these values when you move around the VLBI core. And if you compare this with some simulations and also with the previous analysis that I mentioned before about 3C454.3 from Samanina sub, this can probably be modeled as a BLR being threaded by a larger scale helical magnetic field. Okay, now let me move to how to use Faraday rotation to get an idea of the accretion rate. And if you remember, the rotation measurement depended not only on the magnetic field line of sight, but also on the electron energy density. So you can use that to try to get an idea of what is the accretion rate. And this has been done by Kuo et al. Together with Kichi Asada and Masa Nakamura and collaborators. And they have been observing M87 with SMA at 4 different frequencies around 230 gigahertz. So really some millimeter frequencies. This is the image they got, the SMA image with polarization overplotted. And they were able to feed the EVPAs to lambda square, and they got these values for the rotation measurement with an upper limit of about 710 to the 5th radians per meter square. With this, you can use the measured rotation measurement and get an idea of what is the accretion rate. And this is what they have done. And they obtained a value of about 910 to the 4 solar masses per year. This suggests the ADIOS model, which is the one developed by Blanford and Begelman, the adiabatic inflow-outflow solution, as probably the working model for the accretion in M87. Nice piece of work, but see the error bars, a bit light. So anyway, so what can you do also with Faraday rotation? You can also determine the matter content, and this is by performing polarization observation at different frequencies. And as John Wardle found for 3C279, in which they mapped with the VLBA 3C279, this is total intensity, linearly polarized, and they also found circular polarization. This is the first detection. It was published in Nature, and then Brandeis group has been also detecting circular polarization in many different other sources. Well, the working model for this is that you have conversion from linear to circular, and this requires an intrinsic Faraday rotation, which means that the Faraday rotation is produced within the emitting region. With this, you get an estimation of what the minimum energy of the electrons, and they conclude that this is really smaller than 100. So this is a compelling evidence for the case of 3C279 being mainly made by electron and positrons. We have also been observing M87 with the JVLA. This is work in progress, and we have been able to detect a nice Faraday rotation in Node A, and more surprisingly, this is circular polarization. This is extremely difficult to calibrate, so please this is just a first try, but we are getting a 9 sigma significance with a level of about -1% in Node A. So we had just new JVLA observations to really confirm this, because calibration of this is a pain in the neck. But in any case, it does appear that we could have some circular polarization in M87 as well. Now let me move to some nice simulations by Oliver Porth, and they have been using also GRMHD simulations. In this case, they have been studying further rotation up to sub-millimeter frequencies. You see this, they have been analyzing what will happen between 300 and 700 gigahertz. They have been, they have computed the simulated further rotation, and they were able to, they said, you know, this is a cut across the jet, across the core, this is a cut along the jet, and they said that indeed with EHT simulation, if you have enough angular resolution, you can really observe a helical magnetic field near the black hole. And this simulation also showed that what would be the case of the opacity, the degree of polarization, and rotation measurement as a function of viewing angle. For jets seen just face on, you see this nice polarization with asymmetry around the core, as we saw in BLAC. And also, Sol Molina, for my former student who is going to talk, she's talking next, she found a very similar structure from millimeter VLBI observations in RAO 150. And now let me go very briefly to the last part of my talk. And this is what happens if we actually manage to increase our sensitivity at millimeter wavelengths. And this is just an example of the kind of studies we can perform. So if we come back to the helical magnetic field, as we mentioned before, in this case, you also need to take into account that the synchrotron emissivity is a function of the sinus or the angle between the magnetic field and the line of sight in the fluid frame. So imagine that you have a helical magnetic field. In this case, the top and the bottom will have a significantly different sinus. Here, significantly different values. And you have a maximum asymmetry when the observing angle in the fluid frame is equal to the helical pitch angle, or pi minus that. And the asymmetry will reverse for a velocity which is equal to the cosinus of the angle. So we did some simulations, and together also Eric Clausen-Brown has been studying this, and these are cuts across the jet width or total intensity in polarized flux. So you do expect that one side of the jet will be brighter than the other side. Can we study this with current even centimeter VLBI arrays? Probably not. Why? This is, let me give you a flavor of why that's the case. These are 7 millimeter observations from the VLBI view blazars of 3C273. This is the movie of 3 years. What do you see here is the usual VLBI core, and you see just knots moving down the jet. You don't really see the underlying jet. It is very difficult to see any emission that corresponds to the actual jet and not the knots. You only see the peaks. You know, it's like the icebergs and the Titanic. You only see the peaks. You don't see what is under that. What about if you combine the whole thing? What if you increase your sensitivity? Then you get a completely different picture. And this is a combination of 3 years of imaging, and the total intensity is the stacking of all the total intensity flux. And you see, you start seeing a lot of emission that you are not seeing in just one single epoch. But look at the color scale, which indicates the degree of polarization. You see that components are passing by, and they are mapping the underlying magnetic field. You only see the peaks, but as you have many different components passing by, they allow you to map the underlying jet. And this is what you get. You see it with time how this is filled, and you get an idea of what is the structure. If you combine the 3 years of observation, this is the mean total flux, and you see now you are seeing a lot more things. And then you perform a cut here, you don't see any asymmetry, but if you go at around 3 milliseconds, then you see that one side of the jet is always significantly brighter than the other one. So this is the kind of studies that we could perform with much higher angular, much higher sensitivities. For the Mojave data is even perhaps more astonishing. These are now 14 years. And these are, 15 gigahertz images, 3C279, moving components. 15 gigahertz has a significantly higher sensitivity than that 7 millimeter, but still you only see mainly the knots. And this is what you will see if you combine all these observations. Look at how the moving of components are filling all the degree of polarization. They are tracing that. You see that there is some variation across the jet width. Polarization is always larger on the edges, smaller on the axis, and then you get an idea of what is the polarization and total intensity. And this is the combination of 14 years of 3C273, and very nicely, you see that at 3 milliseconds from the core, you see this offset of emission. If you remember 43, very similar, completely different data sets, completely different frequency, different observers, same result. So you can perform a very interesting study of opacity across the jet width. And with the Mojave data, you can also see that the side that it's brighter shifts with distance from the core, which is maybe an indication of acceleration of a component as has been observed. Remember that there is a reversal in the symmetry when the velocity is close to the cosinus of the viewing angle. And this is, for instance, the 14 years mean degree of polarization across the jet width. Then you do see, this structure that you didn't see that before, and they are very similar to different frequencies. So this is just the summary. Observational increasingly shorter millimeter wavelengths provide these obvious benefits of higher angular resolution, less opacity. I think the source frequency phase reference technique is really useful for increasing the sensitivity, and these are the kind of studies we could hope to be performing. Combination of multi-frequency VLBI observations and this source frequency phase reference technique can, provide information about the jet formation, as we saw through the enhanced angular resolution and less opacity. Determine the three-dimensional structure of the magnetic field in the vicinity of a central black hole. Study the accretion rate. You can also determine the jet matter content and also analyze stratification for velocities and orientation. And that's all. Thank you very much.
I'd just like to caution a bit against getting too excited about helical fields on the scales of something like the 3C273 jet, which is a very large distance away from the nucleus. And two issues that come to mind. One is the flux conservation problem. So whilst I'd be entirely happy with the toroidal field component, advected from the nucleus at that distance, having a significant poloidal component on there would be very, very suspicious, because then you have an r⁻² flux dependence all the way into the nucleus. The other point, which I think was coming out of the pictures you were showing, which very nice stacked pictures, is that you do get quite often enhanced polarization on the outside edges of bends. The polarization degree is enhanced on the outside edges of a bend in the jet, and that's suggesting it's deviating from axisymmetry. Maybe it's shearing at the edges, or maybe it's even just adiabatic stretching. So I think there are other reasons, why the field is not actually a global helix on those scales, although it might be closer in.
When you look at the sources being analyzed, for instance, from the Mojave sample, they only found this clear evidence for gradients across the jet width only in 4 sources. And the clear one is just 3C273, which is a very suspicious. So it may be that it's not handicap produced by, it may not be this general trend to have this helical magnetic field at these large distances or not. But toroidal, yes.
Okay, so let's thanks to the speaker. Okay. Precision VLBI astronomic measurement using SFVR observation of VLA. 20 minutes, and I'll give you notice in 5 minutes. Okay.
To go, I have to put here, right?
No, this is just a point.
Okay, okay. Hi. Okay.
Hi, my name is Sol Molina. I am a PhD at the Instituto de Astrofísica de Andalucía, and we are developing this work in close collaboration con José Luis Gómez, Richard Donson, and María Rioja. I am going to talk about the main motivation of this talk. I am going to show the sample of sources that we are using to do this work. After that, we are explain the astrometric technique that we are developing and show some preliminary results. And the main motivation of this work is the study of the nature of the courgettes. There are, José Luis has explained explained that, but I am briefly mention. There are two complementary models to explain the nature of the jet core, and one of these mentioned that the location of the jet core is the place where the jet becomes optically thin. So the position of the jet core shifts with the frequency. This is observed at the centimeters wavelengths, but if we go to millimeter wavelength, the radio core could be correlated with recollimation shock, and in this case, the jet at fixed at a location in the jet. So to study this is very important to have measurements, astrometric measurements of the jet core at millimeter wavelengths, because at 3 millimeters and 7 millimeters we have measured these models, and we can study this. So the sample of sources that we are using are these. These sources are gamma ray emitting AGN, and we have observed with BLBA at centimeter wavelengths and at millimeter wavelengths up to 43 and 86 gigahertz. I am going to explain the observation strategy because it's very important to understand the technique that we are developing. First, we have used a usual phase reference block in which we observe two calibrators and the target at low frequencies. After that, we use a ionospheric block, which is very important to calibrate the ionospheric contribution that Maria have mentioned also. And in this block, we have observed the target at 1.3 gigahertz, 22 gigahertz, and we also use the new C-band Y receivers at the BLBI, and we use 4IF centering in 4.3 gigahertz and 4IF centering in 7.6 gigahertz. After that, we use a frequency phase transfer block, which is very important to calibrate the troposphere. And in this block, we observe the target at the highest frequencies. And we observe at 43 gigahertz and 86 gigahertz, interleave with observation at 22 gigahertz. And finally, we repeat the ionospheric block. So the astrometric technique that we are developing is a new approach to the source frequency phase transfer that Maria have explained, because in this technique we are measure the ionospheric contribution from the observations at L-band, wide C-band, and K-band. We have to calibrate these contributions, which are tropospheric contribution, ionospheric contribution, source structure contribution, astrometric contribution, and instrumental one. So the term of the structure is not very relevant, because in this kind of source we can assume that it's near zero. And this term includes the core shift. So we have to calibrate these three contributions, which are the instrumental contribution, tropospheric, and ionospheric. The instrumental contribution we have calibrated in a usual way. So we have calibrated the instrumental contribution in a scan, and we export the solutions to all the experiment. But the important thing in this technique is the ionospheric contribution, which is the novel part of the technique. And we know that the delays varies with the lambda to square. So if we have data at different wavelengths, we can fit this contribution. This is an example for Hancock antenna. These are the data that we have taken with the VLBA at K-band, wide C-band, and L-band. And with a fit for this data, we can obtain the total electron content of the ionosphere. So this is the values that we have found for each antenna. And with these values, we can calculate the calibrations that we have to do to calibrate the data for the ionospheric contribution at all the frequencies. These are the solution tables that we obtain to calibrate the ionospheric contributions. These are at 22 gigahertz. These are to wide C-band, and these to 1.3 gigahertz. We can see that the calibrations are similar, but the values, the absolute values, are higher at the lower frequency, and the contributions varies with the time. The different colors are the differences between the IFs. So we have determined the ionospheric corrections, and we want to test if these corrections are correct. So for this, we have applied the solution that we have found to the data, and we recalculate the tech values. We have found this, and this means that these are the residual ionospheric contributions, and we see that the residuals are low and near 0.2 tecu, except for some antennas. We can improve these residuals or doing iterations that could improve the calibrations, but we can say that the most of the ionospheric contribution have been removed with this technique and with the observation at these frequencies. So we have only the tropospheric contribution that we have calibrated, and we at low frequency we have calibrated with a usual way with the global fringe fitting in apes, and now we have all the contributions calibrated, and this is the first map that we have obtained at 22 gigahertz. This map don't have any auto-calibration step, only the steps that I have mentioned. So now we can use this technique, but at higher frequencies, because this is at 22 gigahertz. At higher frequencies, the steps in the first part are the same. We calibrate the instrumental part with a fringe in apes. We calibrate the ionospheric contribution with the tech values that we have calculated from the data at the lower frequency. And for the tropospheric corrections, we have used the frequency phase transfer, and the tropospheric phase contributions are proportional to the observation frequency. So if we have the tropospheric phase contribution at a low frequency, for example at 22 gigahertz, we can multiply by a factor, and we can obtain the phase contribution at a higher frequency. In this case, at 43 gigahertz. So we apply this calibration, and we have obtained a first map. This is the 30 map at 43 gigahertz. But the important thing is that to obtain that, we have calibrated the ionospheric part from the feed of the data at L, YC, and K band. And the tropospheric contribution we have calibrated from the data at 22 gigahertz. For obtaining this map, we don't use any auto-calibration. So we have, this is work in progress. So we have to improve some points about the technique, but for example, we can do more iterations to obtain better ionospheric determination, or we can do better tropospheric calibrations using auto-calibrated data. But here we have a detection to the 43 gigahertz. So this implies that is at fair order, we have calculated the ionospheric contribution and the tropospheric contribution, and this image is referred to the 22 gigahertz, so we can measure the course shift between these two frequencies with this kind of images. And an important thing is that we didn't use an external calibrator to do all the calibration, and this is very important to measurements, to interferometric measurements. So this is the first time that we obtain an image at this frequency like this. So I did very briefly the talk, but a summary. Multi-wavelength observations suggest that millimeter wavelength, the core may correspond to a recollimation shock. And to test this, we use observations of sample of AGNs, taking at centimeter and higher frequencies up to 43 and 86 gigahertz. And we are using a new approach of the source frequency phase transfer to calibrate the ionospheric contribution, and this calculate is do with the data at L, YC, and K band. This is very important. And these are the results that we have obtained of the calibration terms. And using these ionospheric terms and the frequency phase transfer, we are able to obtain detections at 43 gigahertz. And this map is related with the data, with the 22 gigahertz data. So it is possible to measure the course shift. And well, we don't need an external calibrator. And this work is in progress, but we expect to obtain astrometric solutions at 86 gigahertz also. So this is the most important thing, that is the first time that we can measure the ionospheric contribution with the observations at data at lower frequencies. Thank you.
Yeah, questions?
Is there a problem when the frequencies are not exact integers of each other? I mean, 43 gigahertz is not an exact integer of 22. So how do you deal with this not integer being? Is that solved, that problem?
Yes, because it's working, right? And in BLBA, the observations are not at some frequencies at the same time. So we do an iteration. yes, iteration in time. So we solve in this way. If we
Yes.
To higher frequencies, we have we try to have an exactly multiples of the frequencies. For example, between 22, 43, and 86. But for low frequencies, this is very difficult. But at high frequency, also is a little difficult, and to have the observation, it was complicated to obtain this radio between 22 and 43 and 86.
Yeah, she's talking about 22 and 43, but it's actually 22 and 44. It's 2.0001, so it's almost exactly twice.
Yeah.
But it's not exactly twice. But you can actually try to shift a little bit your center of frequency.
Just a moment, sorry. Yeah.
It is solved. It's more complicated if you haven't got a non-integer, but we spent a lot of effort trying to make it work for water to SIO, where your frequency ratio is 1.97. So, and we could do it. So we can. It's more tricky, much better if you have an exact integer ratio. But in this data case, the integer ratio is inside the observing band, so you just need to change your reference pixel. That's all.
So it was reference pixel was changed for this data analysis. Will be changed. Okay. Yeah. Yeah. Oh, I didn't know that.
Yes. Maybe I missed that, but did you compare your TEC values to published ones? The tech values, did you compare them to standard published ones, which we will be using in the past, most of the time when we have tried to remove ionospheric contribution at 18 centimeters, for instance?
I don't know.
You know there are published TEC values every half hour or hour in the US? Okay.
Actually, I have a question. Have you compared the residual phase after this ionospheric calibration at 22, 43 gigahertz? And you mean, I assume that if you remove this kind of ionospheric contribution to the data, and then your residual phase give some improvement for this. Have you checked it? Yeah.
In the data, you...
Yeah, in the data.
Yes, I didn't show, but if we apply the calibration, we obtain good phases and this is so you can obtain a map. But we think that maybe some instrumental thing that we have to take into account to improve the technique. Yes.
That's actually my second question. Like that, I mean, for astrometry, we need to align we need to set up the same reference point for astrometry at 22 and 43 and 86. So maybe just a conventional phase manual calibration or something like that. Doesn't. I think I'm not sure whether this is enough for doing this or not. Yeah. Okay. Yeah.
Very short question because I missed the value. When you got this nice image with no self-calibration, how much flux did you recover as compared with the two one? Because Maria reported 87%.
Yes, and the dirty image we have a signal to noise 5 or something like that. It's very poor image, but we think that we have to improve some points about the calibration. For example, the instrumental one, or we can improve doing more iterations to obtain better results with the ionospheric terms, and we think that we could improve this a lot, but it's work in progress. So.
If there is no question, let's thank the speaker. Excuse me. Shall we start? Yeah. Let's start. The last talk of this millimeter wave studies of continuum sources is Pablo Torne, and he's going to talk about the application and challenges of millimeter frequency, multi-frequency and millimeter pulse observations.
Okay. Hello. Can you hear me well with this microphone? Yes. Okay. So yes. My name is Pablo Torne, and I am a final year PhD student in the Max Planck Institute for Radio Astronomy in Bonn. And today I'm going to give a very general talk about pulsars, and I will try to show you, well, pulsars are an uncommon topic for people working at high frequencies, but I want to show you that they are very interesting and that we can do great things also studying them at millimeter wavelengths. And, well, the work I will present is not only mine. I, of course, work with collaborators. There is, yeah, so you can see here some of the people working with us, most of them in the pulsar group in Bonn. And the talk is divided in 4 parts. First, I will give a very brief introduction about pulsars, and then I will tell you the motivation to try to do millimeter pulsar studies. In the third part, talk to you about some of the experiences we got doing millimeter and multi-frequency pulsar observations, and I will finalize talking about the future. So probably you all know this, but well, what is a pulsar? Pulsars are neutron stars that form in supernova explosions, and they are rotating neutron stars, and they emit beam broadband electromagnetic radiation. The key for pulsars is that the rotation axis and the magnetic axis are usually misaligned, and the radiation is produced along the magnetic axis. So if the Earth happens to be on the line of sight of the beam, we will see a pulse as the neutron star rotates. And they are very exotic objects, and we can see this from some of the characteristics of pulsars. Well, neutron stars with masses between 1 and 2 solar masses, in radii between 10 to 12 kilometers, so these are really compact objects with enormous densities that can be higher than the nuclear density. So in fact, the interior of neutron stars is a mystery. They are almost black holes inside. And of course, they possess very strong gravity fields, about 10 to the 11 times the gravity we have on Earth. They also possess the strongest magnetic fields known in the universe, up to 10 to the 15 Gauss. And well, they are very stable, and they can rotate very fast, up to more than 700 times per second. So an overview of the science we can do with pulsars. We can do many different things, most of them fundamental physics. For example, we can study super dense matter or do tests of gravity theories, even try to use pulsars to detect gravitational waves. And well, there are many other things we can do: stellar population, high energy astrophysics, study the interstellar medium, and so on. I'm not, of course, an expert in all these topics. I just want to show you, take-home message that pulsars really allow many different studies in fundamental physics, and they are unique tools in the sense that some experiments can only be done using pulsars and not with other objects. So why would we like to do millimeter pulsar studies? Well, the short answer is that some of the experiments, like for example, well, tests of gravity theories or studying the pulsar emission mechanisms, will benefit of having millimeter data, or even multi-frequency data, for example, also combining millimeter and centimeter wavelengths. I want to give you 2 or 3 examples of this. For example, when we want to study the interstellar medium, we will see some effects on the emission by the pulsars as it travels towards us. For example, the dispersion measure. which is a delay of different frequencies. I'll show you this in the next slide visually, that is produced by the free electrons on the line of sight. Or rotation measure. Jose Luis has already explained this in great detail. We will see a change in the polarization angle of the radiation due to the magnetic field along the line of sight. Or we can have also scattering and scintillation. And the main point here is to see that all these effects depend strongly with frequency. So if we can have multi-frequency observations, and the larger the difference in frequency, we can try to do measurements with very high precision. These are just two visual examples of the pulse dispersion. You cannot see it, but here it's frequency and here is pulse phase that can be traduced to arrival time. And you can see how the lower frequencies arrive delayed with respect to the high frequencies. And this is a textbook example of the temporal scattering of a pulse profile. You see here the emission of the pulsar. And as you go to lower frequencies, this is 1.4 gigahertz, and here you have 250 megahertz. You can see this characteristic exponential tail that is produced by the scattering, spreading the power of the pulsar also across greater pulse phase, and decreasing the detection signal to noise, and sometimes making the pulsar undetectable. Another example is testing gravity. There are many different ways we can do tests of gravity, but the most interesting nowadays are those involving pulsar in the strong field regime. And I point you to these nice results by Kramer et al. In 2006, and also the new paper hopefully coming this year. In our galaxy, the strongest gravity field we have is, of course, in the supermassive black hole at the center of the galaxy. So there is a star. And to do these great gravity experiments, we need first to find a pulsar in close orbit with the supermassive black hole, so we can see the effects of the curved space-time on the pulsars. And without going into much detail, we have a problem, and it is scattering. As I showed you before, it can render the pulsars undetectable. And it is a problem not yet well understood. And I give you here a couple of references if you want to check why we still don't understand well what is going on. But the message, or the key, is that the scattering has a very strong dependence with frequency. And so if we go to high frequencies, we will greatly decrease the effect of scattering. And this is very good to observe through very dense mediums, like the galactic center. And it's perfect then to try to observe, search for pulsars, and observe them, study them in the galactic center. Third and last example is about the pulsar emission mechanism. We discovered pulsar 45 years ago, but we still don't understand well how they emit the radio emission. And just, it's a bit messy, the slide, but the message is, well, some models, for example, predict that the coherent mechanism that produces part of the emission from pulsars will not be efficient anymore at some frequencies, and we might be able to detect an incoherent component of the emission. Some works have shown already strange effects at very high frequencies, and unfortunately we don't have many of these observations because pulsars are very faint. I'll go to that in one or two slides. But you can see here that in the 90s already something weird seems to be happening at tens of gigahertz, very similar to what the models predicted. And another example is the profile evolution. So when the profile of a pulsar has multiple components, they tend to go closer as you go to higher frequencies. This is related with the fact that some models predict that the high frequencies are produced deep down in the magnetosphere of the pulsar. But some theories predict that there will be a saturation. At some point, the profile won't evolve more. The idea, again, is all these effects depend on frequency. And so if we want to study them, we have to go to higher frequencies, in some cases, the millimeter regime. There has been other effects like unexpected depolarization, also observed at high frequencies, and also flux density variabilities that are not common or seen at centimeter wavelengths. So the take-home message would be here that there is a strong frequency dependence in many effects, and therefore multi-frequency and millimeter data are very variable for some experiments and key in others. So there are some questions we can only answer if we have millimeter or multi-frequency pulsar observations. So now a bit of our experiences doing multi-frequency and millimeter pulsar observations, and I will also try to summarize the challenges that we had. The biggest challenge, in my opinion, is, well, that pulsars are very steep spectral sources. Usually we can describe their spectrum as a single power law, so the flux density is proportional to the frequency with a spectral index, and there are several works studying the pulsar population given a mean spectral index of -1.4 or -1.6. This means, as you can see here, that the flux density decreases very rapidly with frequency. So it is important to have in mind that pulsars are extremely faint at high radio frequencies, with flux densities that can go down to pico-Jansky, so really faint. There is one exception though, and it's radio-loud magnetars. The magnetars are very rare pulsars that show extreme magnetic fields. We only know 25 magnetars now. They are mostly detected in high energies, X-ray and gamma rays, but some of them are also detected in radio. These are even rarer. Only 4 are known now. And the peculiar characteristic is that they show a flat spectrum. So you have here an example of the magnetar found recently in the galactic center. I will talk about this source a little bit more in the next slide. And you can see the spectral index measured was -0.4, which is much flatter than the average of -1.6. This makes radio loud magnetars ideal for millimeter observations. And I want to give a couple of slides to this object because it is very interesting. It was discovered in 2013 in X-ray and then in gamma rays. And after that, it was detected also in radio with the FSPEC and ATCAR telescopes. The most important thing is its location. It is just 0.1 arc-seconds away from Sagittarius A star, with a statistical projected distance of about 0.12 parsecs, making it by far the closest pulsar to the supermassive black hole. Because it is a radio-loud magnetar, it is ideal to try to test of pulsar millimeter observations in the galactic center. And our team has been monitoring the source at centimeter wavelength since its discovery. But we also did one campaign of simultaneous multi-frequency observations using NANSE, FSB, and the IRAM 30 meter, plus a test observation with APEX. A summary of nice results coming from these objects. It allowed us to measure a magnetic field that was stronger than what it, well, we didn't know, but it was strong. And this had implications for accretion and jet formation processes. Also, the scattering toward the galactic center has been revised. This was thought as the major problem why we couldn't find pulsars around the supermassive black hole for 20 or 30 years. And the new observations have shown scattering that is over 3 orders of magnitude smaller than what was thought during 30 years. And we were also able to measure the emission properties of the magnetar with detections down to 0.9 millimeters, which are the new record of the detections of any pulsar in the radio band, doubling basically the previous record in 2007. And this, although you cannot see it very well from behind, but this shows you the pulse profiles of the detections of this object from 1.5 gigahertz with Jordan bank, going up to 19 gigahertz in the initial discovery in the radio. You can see the detection at 1.4 is very weak due to scattering. The pulsar theoretically should be stronger at the low frequencies. And as one increases the frequency of observation, the scattering gets kind of, well, it decreases and then you can detect it better. These are the results of the simultaneous campaign going from NANSE up to 225 gigahertz. That was the new record those time. It was published in April this year. And these are the preliminary results of what I'm doing now with a new campaign with the IRAM 30 meter detected the magnetar down to 300 gigahertz more or less. It's a very weak detection, but the fact that it is aligned with the simultaneous observations at lower frequencies really give this much more significance to the detection. So here I want to try to summarize what were the challenges that we had. Maybe this is interesting for further discussions during the workshop. Thanks. The main challenge, well, is of course the faintness of the pulsars at high frequencies. This means that we require large collecting areas that are not very common in the millimeter world. and also very long integration times. And this is funny because, for example, for Pico Veleta, we needed to slightly modify the control software of the telescope because it didn't allow to do tracks of 1 or 2 hours in continuum mode on a source. This mode just didn't exist. Also because pulsars are broadband and transient objects, we cannot use the standard atmospheric removal and calibration techniques in the millimeter observatories, like frequency switching or position switching. Because if you use frequency switching, you will subtract the entire pulsar, and for position switching, you will need to synchronize the observation with the rotation of the neutron star to avoid being off source when the pulsation is arriving. And in many cases, the telescope won't be able to switch even with a wobbler fast enough to follow a rotation of a pulsar that rotates hundreds of times per second. This, of course, meant that in the data we had all the atmospheric effects, all the variations, so we have a horrible change in the mean count level, and also the self-produced RFI. For example, one good example is a very strong 1 Hz signal coming from the cryogenerator, we think. The pump makes the precise flux density calibration very tricky. So we are developing new code and new techniques to do this. Another issue that we are facing is that because in the millimeter facilities, they usually don't have a specific pulsar backends, sometimes the timestamps, so for some pulsar experiments, we really need to be 100% sure that the timestamp is accurate. And when you want to combine with different observatories or different backends, that seems to not be an easy thing, because we are not using VLBI backends. So these are just standard backends, at least for our test. And well, of course, and I'm sure we will talk more about this, is the weather, but we cannot control that. And also synchronize being on source at different observatories at the same time, which is mostly limited by the millimeter facilities that spend a large overhead in pointing, focusing, and calibration measurements. And just 2 slides to finalize. Where do we go from now? I think the future is really great for pulsar astronomy, mainly thanks to more sensitive facilities that are coming online. For example, the 30-meter telescope that is always being upgraded, and it is a great telescope, allowed us to do these good experiments. But also NOEMA, the LMT, or ALMA. And my last slide goes to black hole cam, which is a big effort to study gravity using images of the supermassive black hole of the galactic center. And important is that it includes the search for pulsars around this supermassive black hole that will complement the results by the image. And pulsars are potentially it's a great experiment if we find one, because we can measure the mass, the spin, and the quadrupole moment of the black hole with a much precision. And in fact, today there is a paper in the archive just published this morning from Pesaltis, Vex, and Kramer that explains you how this is going to be done, not only with pulsars, but combining the image and the S-stars measurements. Of course, Black Hole Cam is in global collaboration within the Event Horizon Telescope, that I'm sure we will know much more about these great projects in other talks. And this is my summary, just to wrap up. Pulsars are very interesting tools for fundamental physics. And the millimeter observations of pulsars are not common, mostly because they are very faint. But nowadays, thanks to the upgrades in telescope, we can observe some of them. And I hope you have seen also briefly that there are very interesting experiments that we can do using millimeter data or multi-frequency data. Radio-loud magnetars are a special case that show a flat spectra. We have found one very close to Sagittarius A star, and this is great. We can use it for doing tests and experiments using pulsars in the galactic center. New millimeter facilities or upgrades on existing ones are increasing the sensitivity of the observatories, allowing to observe other pulsars that are too faint to be observed nowadays. So with time, we will be able to observe more pulsars. And of course, I think the Event Horizon Telescope and Black Hole Cam will really revolutionize the studies of gravity. And for this fantastic project, pulsars can be key. We just need to find one close enough to the supermassive black hole. That's it. Thank you.
Thank you. Questions? Question.
So what is the evidence that the magnetar near the galactic center is actually at the same distance?
Sorry, can you repeat that?
What is the evidence that the magnetar apparently close to the galactic center is actually at the same distance?
Yes, that's a good question that I also did. So apparently, because I haven't done that study, but I asked the same question, they have done statistical studies, and there is evidence that the magnetar has to be at that distance. It cannot be farther back or very close. Other reasons is that the scattering of the image of the magnetar is exactly the same as the one in Sagittarius A star, telling you that they should be behind the same medium. And a third reason is by BLVI studies, one see the magnetar following the same trend of all the stars that are rotating around the black hole. And I guess for the stars, they can measure the distance with more precision. And these are the three reasons why they reached this conclusion. They told me that there is one in a million they are Bauer, I don't know the name, the surname is Bauer, doing the experiments with the BLVI in the US, and Rafe Etoch, which is the leader of the Nature paper of 2013. Those were the ones doing the main jobs. No, I think the scattering screen is what they conclude. The scattering screen is halfway, not the magnetar. So the controversy, and this is why I said that we still don't understand the scattering well, is that one study says the screen is close to the supermassive black hole, the other study says it is halfway. So there are still things we don't understand, but not the object.
Yeah.
So what is the right strategy for finding millisecond pulsars close to the galactic center? I mean, one way you can do this is if you're doing a VLBI experiment on Sagittarius A star anyway, is to use the phased sum from ALMA as your, to search for pulsar signals. Is that the best way, or are there other things that we should be thinking about?
Yes, so the best way, okay, in the past, because of the scattering, we thought we would never see millisecond pulsars. The new studies have shown that that is not true. There is always a trade-off between the observing frequency and the scattering. So let's assume the scattering allows us to find millisecond pulsars. The key is collecting area. The more collecting area, the better. That is why phased ALMA would be the best instrument to do this. When you do interferometry, you also do your beam smaller, so you take less background emission, so better. And the searching techniques, the software, let's say, we know it already. So,
I mean, what sort of wavelength is optimum here? Is it 3 millimeters or is it shorter?
It is a good question. Pulsars are steep spectral sources, so the lower the frequency, the much stronger they are. But of course, the lower the frequency, the worse interstellar medium effects you have. So until now, there has been many searches up to, let's say, 10 gigahertz, 15 gigahertz, they found nothing. And we don't know why. So the idea now is to push it to higher and higher frequencies without a real good reason. Maybe the scattering is not well understood. It is affecting the high frequencies more than what we think. So we will try 40, 50 gigahertz and then 3 millimeters with black hole cam, taking advantage, of course, of all the effort by Event Horizon Telescope and so on.
Yes, thank you. And let's thank the speaker again. Then maybe the next session is chair is Do Yong-byun. Yes, thank you.
Okay, my name is Do Yong-byun. I'm from Kasi in Korea. So this session is on the 3 millimeter VLBI studies and key science cases, especially for on lines observation. First speaker is Valentin Buharabal. Okay, thank you. The title is Applications of Multi-Frequency Millimeter VLBI to the Study of Evolved Stars. Okay.
Yes, so my talk deals with the in particular, we will focus on the importance of good astronomy. Okay. As you know, evolved stars, mainly AGB stars and red supergiants, are losing material. Okay, thank you, thank you. These stars are pulsating, and the pulsation in some way propagates through the outer atmosphere by means of a series of shocks up to some point in which the temperature drops enough to form dust grains. And when grains are formed, then the radiation pressure is able to push the whole layer, which soon reaches its final expansion velocity of about 10 or 20 kilometers per second. SIO masers and water vapor masers are precisely coming from these regions, and therefore are very useful to study all these crucial phenomena. These are the very first accurate maps of an AGB stars in SIO maser emission. Is TX-CAM. You see this beautiful ring structure, which is due to tangential amplification, and also you can see that really it comes from these inner circumstellar regions I mentioned. In this figure, you can see hydrodynamical calculations of how the inner atmosphere, the outer atmosphere is pulsating, and how, in the end, the gas escapes. And this is an observation in which you can see these phenomena, but this is part of the famous movie by Phil Diamond and colleagues of TX-CAM. You can see how the radius of the ring is increasing because the shock is advancing. At some point, there is a new shock advancing from inner regions, and also sometimes you see chaotic movements because finally this series of shocks is a complex thing. Okay, these are water vapor observations. They are coming from a wider region. From analysis, what you see here is the SIO ring, right, in these sources. From the analysis of the velocity of the spots, we know that really the water vapor maser is coming from a region which is already in expansion, in a clear expansion, right? You see that the SIO ring is significantly smaller. The astrometry of water vapor observation, the water vapor observations here is good because I think it's Merlin, but that of SIO is not really accurate. So we are assuming that the centroid of the ring is coincident with the center of the star to put the SIO here, and you will see similar assumptions several times in my talk. Okay, before continuing with the analysis of the physical conditions from observations of SIO, we should understand a little how is the pumping behaving of these lines. The SIO masers are always rotational transitions in vibrationally excited states. We can see the J120 at 7 millimeters wavelength, J221, J322, etc. in V equal 1, V equal 2, V equal 3, and V equal 4 states, right? The inversion of the populations is thought to be due to trapping in the raw vibrational components of the vibrational transition at 8 microns. It is easy to show that when these transitions are optically thick, we systematically overpopulate the high J levels just because the de-excitation is less efficient for higher J transitions. So we systematically will have a chain of masers across the rotational ladders of the excited vibrational states. Which is different depending on the model, is if the population of the high V states is due to collisions or is radiative. Depending on this collisional or radiative pumping, we have, of course, different results of the calculations. These are very old calculations, but finally, new results more or less give the same things. Of course, the collisional pumping requires a higher density. And also know that the radiative pumping is able to discriminate better between V=1 and V=2 lines. These are the two lowest V=1 lines, and these other lines are for the V=2. So, in principle, if pumping is radiative, the V=2 and V=2 measures should come from different regions. What happens when we observe actually these measures? This is V=2 J120, and this is the V=1 transition. You see that the V=2 ring is slightly smaller as expected because it requires a higher density. And you see that the clusters of spots for both transitions are very similar. However, the spots are very rarely coincident. You can see that better in IRC plus 10011, which is this star. Here, the grays is V=1 J120, and the contours is V=2 J120. Note that more or less the clusters are the same, but the spots are not coincident. In particular, look at the southern clamp. When you see the maps per velocity channel, one has the impression that the V=2 measure is actually dancing around the V=1 component, but it's never coincident with the position of the V=1 line. Anyway, these are very good maps with resolution well under the millisecond and with a high signal to noise, but the relative positions are not accurate. Rheostometry is not accurate, so we are not sure on how we should place the one transition with respect to the other. So, under these conditions, can we conclude that the pumping is radiative or collisional? Can we say that the density is as high as 10 to the 10 centimeters to the -3, or can we say that the density must vary by a factor 10 in 1 millisecond, which means 1/10 of the stellar radius? And also note, in this spot, in this condensation, in fact, it cannot be a condensation, because V=2 is always in the outer part, and V=2 J120 requires a higher density. So instead of the condensation, it could be a minimum of the density. Is really difficult to believe. All these problems come because really we don't have an accurate astrometry. Of course, accurate astrometry can be obtained in particular thanks to Vera. These are Vera observations. In R. Leo minoris, for instance, you can see more or less the same results. The clusters of spots are very similar, but the spots are not coincident. Anyhow, these observations, even with Vera, are not easy at all, and I think that in this source they had to transfer the phase from 22 gigahertz because the calibrator was too weak. Is that true, Richard? The 7 or Maria? The problem here is the weakness of the phase calibrators. Okay, also the Korean VLBI network is able to obtain good astrometry. This is again R. Leo minoris. You see more or less the same results with clusters of spots, but not exactly coincident, the spots. And in this case, again, the phase is transferred from 22 gigahertz. So we also have a measure we also have the distribution of the water vapor measure. But unfortunately, in this case, we only see a few spots. So we can't be sure about the relative distribution of water vapor measures with respect to SIO. Again, note that although the astrometry is very accurate in this case, these observations with the small arrays are not as impressive as the others I have shown you. This is the beam, is really not as good as it can be obtained with transocean baselines. I have to mention that there is a KVN multi-frequency observation program which is already going on, and which will be presented by Du Jung Byum in this afternoon, I think. Okay, other lines. V equal 3 J120, also at 7 millimeters. This is an important, a very interesting line, which has been already observed, and I hope will be observed in the future. One would expect this transition to be placed in a completely different spots, in a completely different region than the other lines, because really it requires a very high excitation. V equal 3 is placed at more than 5,000 Kelvin over the ground, so really the excitation of the lines of this line is very hard, and one would expect this 7 millimeter line to be very different in distribution than the others, but in fact it's not the case. As you see, the results of V equal 3, which is the red contours there, is absolutely similar to the other two lines, 7 millimeter lines, in the same clusters, again with rare coincidence, but we don't see any significant difference with respect to the other lines. Another line which can be observed is V equal 1 J221. This is a 3 millimeter wavelength. It's a difficult observation. In this case, the fraction of the lost flux is very important, and of course we have no accurate astrometry. We expected this line to show a very similar distribution to that of V equal 1 J120, because both belong to the same maser chain. They are excited with a very similar energy, and they are pumped by a very similar process. So we would expect more or less the same for the 7 millimeter and the 3 millimeter lines. However, it's not the case. You can see V equal 1 J120, the V equal 2 J120 in R. Leonis, and the V equal 1 J221, which is clearly occupying a wider region and with a spot distribution which is clearly different. In this source, again, is IRC 10011. We can see, well, this is the image I have already shown you. In grays, V equal 1 J120, and in contours, V equal 2 J120. And this is the distribution of V equal 1 J120 versus the 3 millimeters line. And you can, well, the scale is not the same in both images. You can see that clearly the V equal 1 J221 is placed in an outer region, and the distribution of spots is completely different from that we have seen in the J120 transitions. So again, this is a completely unexpected result that cannot be explained by simple standard models of SIO maser pumping. Let me show you a possible explanation of this phenomena, which is the presence of line overlap, in this case between lines of SIO and water vapor. In the simple excitation model, which is represented here, we can see V equal 1 J221 and J120, V equal 2 and V equal 3. Of course, the intensity depends a lot on the density, and the V equal 1 requires the lowest density. When we introduce the line overlap, what we see is that the V equal 1 J120 is shifted and is now practically coincident with the V equal 2 and V equal 3 7 millimeter lines, the other 7 millimeter lines. However, the V equal 1 J221, the 3 millimeter lines, is practically not affected by this phenomenon and now remains in a completely different region of densities, probably it's a lower density, so probably in an outer region. So line overlap could help, but let me explain a little what is line overlap. In this case, what we have is a couple of lines. One of them is a raw vibrational line of water vapor, and by a lucky coincidence, the frequency of this line is practically the same as the frequency of this transition of SIO, such that the photons emitted by water vapor can be absorbed by SIO by this transition of SIO, right? Which is the result? Molecules are transferred from that level to this level here, and therefore we introduce a strong coupling between this transition, the V equal 1, J1 to 0, and this one, the V equal 2, J1 to 0, explaining the shift of the V equal 1 I have shown you in the calculations. On the other hand, of course, the G equal 2, J1 to 0 is practically not affected, and note that since we are overpopulating the G equal 1 level here, we destroy the measure between G equal 2 and G equal 1. This, in fact, this is actually observed, and this measure is very weak and rarely observed in evolved stars. This method, this procedure, was originally developed to explain the anomalously weak emission of this transition by Hans Olofsson et al. But we can see that, in fact, it can also explain, at least qualitatively, the rest of the observational results. Always keeping in mind the observational problems I've mentioned, and of course the theoretical uncertainties. Okay, let's move to more evolved objects. Planetary nebulae. As you know, planetary nebulae with the white dwarf in the center are the result of the evolution from an AGB star with its circumstellar envelope. It's a very spectacular phenomenon that takes place in less than 1,000 years. And okay, what we see here is an AGB star with a circumstellar envelope. You see the circumstellar envelope is practically spherical with these arcs or even spiral, which are these spirals are often observed in objects of this kind. And this object is a very young planetary nebula, is CRL 2688. You see that the outer part of the nebula is still spherical with the arcs, but there is an incipient axial symmetry developing from the inner parts. And what we see here, what we have here is a couple of holes through which the stellar radiation can escape and illuminate the outer parts of the shell. What we see here are just light beams. This source is OH231.8, also known as the Calabash Nebula. In this case, the bipolar structure is much more developed, but curiously, also in this case, the central star, which is by there, seems to be less evolved than for CRL 2688. What we see here is a very fast, in yellow, is a very fast and cold bipolar outflow, which is detected in CO emission and emission of other molecules, and which can reach velocities as high as 400 kilometers per second. The blue component is ionized. And finally, this is NGC 2346, which is an evolved planetary nebula. In this case, you see this typical hourglass structure, which is the result of the evolution of the bipolar one we have seen, and also this strong and dominant torus in the equator. How all this can occur? Okay, I've said that AGB stars are losing material. In fact, the mass lost is so important that by the end of their lives, they have ejected all their stellar envelope, which means most of the initial mass. It means that really the star has ejected itself, and really the star is not now here, but there, right? Finally, all the stellar envelope is ejected, and we can see the core, which will be the new white dwarf in the center of the nebula. These new white dwarfs are able to eject two very fast and collimated outflows, probably due to reaccretion from a rotating disk. Such a rotating disk can only exist if we assume that there is a binary system, because we would need angular momentum to form the rotating disk. Okay, of course, this fast bipolar outflow shocks the fossil circumstellar envelope ejected in the past AGB phase, and the resulting shocks originate the bipolar structure, which in a short time becomes something like an hourglass with a very dense torus in the equator. Well, this picture I have shown you is far for being really well established. It's the best we have by now, but really many issues are not well understood in the evolution of AGBs and the formation of planetary nebulae. Okay, let's come back to the Calabash Nebula. It's one of the few sources in which we can see SIO masers, one of the few planetary nebulae in which we can see SIO masers. The SIO masers here have a couple of spectral features, one of them coming from these spots, the other coming from those spots, and again, the circle is the expected size of the central star. What you see is that really these spots look like a rotating disk around the star, the rotating disk we want to find, and also the velocities and the intensities are roughly compatible with expectations from emission by a rotating, perhaps accreting disk. It was at that time the first tentative detection of a Keplerian disk in a post-AGB object. Water emission in this object, we also see two spectral features, but in this case they come from the outflow. I mean, they are aligned in the sense of the bipolar large-scale outflow. When SIO was tentatively placed in the middle of these water vapor features, what we see is exactly what we want to see. The bipolar outflow described by water vapor and the rotating disk in the middle around the star. Both the velocities and the distribution of water are absolutely compatible with being coming from the base of the bipolar outflow. But again, the relative positions are poorly known, particularly for SIO. In fact, these people have been trying to improve astrometry, repeating the observations, and also observing with connected interferometry, and the last result that they have found, always very uncertain, is that SIO would be placed at 250 milliseconds from water. This is absolutely incompatible with the ideas we had in, a priori, and really we cannot put that in the scenario I have shown you before. Anyway, all this is very tentative. After many years, more than 10 years, they are still discussing this topic, and this is a picture I got a few days ago. Is the whiteboard of one of these guys, and you see, more than 10 years ago, they got these observations, and they are still now discussing if the distance between water and SIO is 250 milliseconds, 200 milliseconds, or nothing. So you see the importance of obtaining good astrometry once and forever. Okay, so my conclusions. Of course, multi-frequency VLBI observations can be done at present, sometimes with good absolute astrometry, but it's always difficult, even at 7 millimeters. Not many results have been published, and it's really very hard at higher frequencies, and by the moment it's practically impossible to perform very good astrometry at these frequencies, and mainly if we want to observe with long baselines. However, such observations would be very important to study the inner layers around AGB stars, where grain formation and mass loss is actually taking place, to study the SIO pumping mechanism, which are still debated, and to study the inner regions of post-AGB nebula that you see are very interesting to understand the end of the AGB and the birth of planetary nebulae. I hope from what we are listening, we are seeing here, that in the near future we will be able to perform systematic observations of several lines, particularly at high frequency, and particularly with good astrometry. So that I think that's all. Thank you very much.
Thank you. Yes, we have 10 minutes for discussion. Is there any question or comment? Yes.
How many other planetary nebula are there? I mean, can you estimate the number of objects which emit at SIO?
I think that At present, there are 5 objects detected in SIO, and there are now several programs going on to extend the number of nebulae detected. But it is normal if we can detect SIO because in these objects, because SIO is always formed. I mean, the maser always arise from regions very close to the star. But in planetary nebulae, these regions are practically empty. So when you have a more or less developed planetary nebula, a well-developed planetary nebula, you don't expect to have material close to the star to emit in SIO. So in principle, it's something to be detected just in very young planetary nebulae.
Okay, any question? Okay, I have. Okay.
So this unexpected misalignment between in the planetary nebula of the water maser and SIO, so surprising, it really might affect all the previous observations as well. I mean, it might be that case because they've always been aligned, the water and the SIO masers just like that, in concentric circles. Isn't it?
You mean, for instance, in
evolved stars,
in AGB stars?
Yes.
One could have. Well, first of all, we know it's not the case, because in some cases we have good astrometry, and in these cases we see that the optical positions and the SIO center, I mean the SIO ring center, are coincident. So in those cases, for instance, in your observations of R. Leo Minoris and others, and a few others, really they are coincident. So we can extrapolate that to all the stars and saying that really the star is in the center. And in the case of water, we know that the star is in the center because we have good astrometry observations. So in AGB stars, really, we don't expect a phenomenon of this kind. In this case, really, it's very surprising because what does it mean? It means that the star is there and the outflow comes from what? From nothing. So really, it's very surprising. And also in the case of the Calabash, it happens that the SIO masers are fading since some years ago. So because they didn't obtain a good astrometry at that time, now it's very difficult because now it's not detectable. For that, it's also interesting to improve the sensitivity of BLBI at 7 millimeters. So what you mentioned about a high sensitivity thanks to phase transfer is important because precisely in this prototype, in this important case, it happens that the SIO masers are fading, and it's not impossible that they will not be detectable in the future, just because the source is evolving to a state in which we don't expect the SIO masers.
What was the instrument? No, it's just a single question. What was the instrument that had that detection?
Do you mean the SIO observation? Is the BLBA. I think so, yes.
Okay, I have one question. You showed some comparison of the spatial distribution of J equal 2 to 1 and J equal 1 to 0 transitions.
Yes.
Could you say some word about J equal 3 to 2 transition?
The problem is I don't know published observations of J3 to 2. So I can't tell you if it is similar or not, but I am convinced that in the near future they will be obtained because you are succeeding transferring phase from 22 to 130 gigahertz. So certainly now it's feasible to observe the 2 millimeter masers. It is at 2 millimeters. It's not an easy observation, but if you manage to handle the phases adequately for that case, probably the results will come soon. I hope.
Okay. Thank you. If there is no other question, let's thanks to the speaker again. Okay, next speaker is Luca Moscadelli The title is Studies of Star-Forming Regions Using Multi-Frequency Maze Observations. This is also invited talk, so 25 minutes will be given for presentation and 10 minutes for discussion.
Can you hear me? Okay, hello everybody. I would like to show you the molecular measure are important tool to study star formation. Star formation, which present model indicate that involve a specific kinematic structure as accretion disk and jet collimated along the derotation axis. And another important ingredient should be magnetic field that are relevant in collimating and accelerating the jet. The structure of my talk, first I will describe the centimeter wavelength molecular measure to describe their role in studying with high accuracy, 10 AU from the forming star, the kinematic and the magnetic field. Such higher linear resolution cannot be achieved even with the best present millimeter interferometer. Then I move, considering the millimeter wavelength molecular measure, their contribution is relevant in adding information also about the physical condition of the gas, then to better sample using different measure lines the gas kinematic and magnetic field, and finally to speed up the proper motion measurement by large factor, taking advantage of the higher angular resolution of millimeter VLBI. This plot shows a distribution of the strongest and most commonly observed centimeter wavelength measure. The OH 1.6 gigahertz in star forming region. OH 1.6 gigahertz, methanol exists at 12 gigahertz, and water at 22 gigahertz. This distribution, given with a different color, shows that generally these measures are distributed radii of a few hundred U from the forming star. Here probably best peak by the millimeter continuum peak. The measure emission constitutes of single emission center compact enough to be studied with VLBI to derive also the proper motion with multi-epoch observation, which combined with the lanocyte velocity give the full 3D kinematic of the gas. And generally, each measure species trace a different kinematic structure. Let's have a look in detail in this source. It's G23, that is a high mass protostar of a estimated mass of 20 solar masses. Recent subdelimiter array observation have observed a collimated CO outflow, here depicted with integrated intensity blue shifted and reshifted emission on scale of a few tenths of arsec. And just at the center, the SMA has detected a compact millimeter continuum. At the center of the millimeter continuum, multi-epoch VLBA observation has derived the distribution of the water measure, here given by colored triangle, with color representing the lanocyte velocity. There are three clusters elongated from northeast to south-southwest, parallel to the axis of the large-scale molecular flow, and the northeast cluster has proper motion, if you can see the arrow, the colored arrow here, that are moving to northeast. So it's quite clear that the water measures are tracing a jet, a collimated jet, that is powering the larger scale molecular outflow. But they give also another information, since the cluster at the center show an arc-like distribution with a proper motion, the arrow here, that is diverging from the center of the arc, where is probably located the unstellar object. So together with the collimated flow, there is also a wide-angle wind emerging from the unstellar object at a radius of about 1000 AU. Since the methanol maser are all around the distribution of the arc-like feature of water maser here in red, we should expect that they could be helpful in tracing the action of the wide-angle wind on the surrounding gas. We have observed the 6 GHz methanol maser using multi-epoch EVN observation, deriving very proper motion, shown here with cone, to give also an idea of the accuracy in, on the better uncertainty in the direction of motion. The pattern of 3D velocity is quite complex, but we think that the methanol maser are tracing the rotation of the envelope surrounding the protostar around the jet axis, here indicated by the dotted line, and also radial expansion. Hints for rotation comes from the fact that the proper motion of spots that are projected closer to the jet tend to be transversal to the jet, while the proper motion that should be found closer to the equatorial plane are moving radially away. And certainly the expansion of the trace by the methanol maser has to be in relation with the wide-angle wind that we have first traced with the water maser. Nowadays, three-dimensional magnetic hydrodynamic model are reaching enough linear resolution to give a full description of the kinematic and magnetic field around the protostar at radii of 1000 IU. This is a model from Seifried, collaborator, that at 4,000 here from the start of the collapse of 100 solar mass core show the presence of a flattened density distribution embedded with magnetic field, the white contour here. And the accretion flow and the ejection flow appear to be pretty collinear, parallel with the magnetic field. So this model predicts that the velocity and B vector should be approximately parallel. We can actually directly test this model using methanol maser in G23. This plot again gives the distribution of the 6 GHz methanol maser in G23, and we have recently performed the measurement of their polarization. Generally, a few percent, they are polarized at a few percent level. And for each, this is just a zoom of the central area here. And for each maser spot, for each we have detected polarization, is plotted here the black segment to give the polarization angle, and the red segment to indicate the orientation of the proper motion. Note that the magnetic field are expected to be perpendicular to the polarization vector. This plot shows the distribution of the difference between the position angle of the polarization and velocity vector versus the position angle of the maser spot as seen from the young stellar object. You can note that the points here are not spread randomly, but tend to concentrate around about an average value of about 60 degrees with a relatively small dispersion. That translates in the result that the velocity vector velocity vector should be tilted by, on average, 30 degrees from the magnetic field. So we actually don't find the result predicted by the previous model, but consider that even turbulent velocity field of a few kilometers per second in amplitude could produce this tilt of the velocity vector from the magnetic field. So I think that it's important to pursue this kind of observation. I take this slide from a recent result from Gabriele Sursis which has recently completed observation of about 20 methanol masers in polarization using DFVN, and we have started now a program to measure the proper motion in all these sources in order to extend the comparison of the B and V field in a sufficient large number of objects to be representative for the study of high mass star formation. So to resume what I've said till now, I think that I have provided enough indication that a centimeter wavelength molecular maser are important to have unique information about the kinematic and the properties of the magnetic field. Next, I move considering the millimeter wavelength maser. About 18 methanol maser have been observed over a frequency range from the 6 to 12 gigahertz, the strongest one that I've described before, a centimeter wavelength, up to 230 gigahertz. Several sources are found to be stronger multi-maser emitter in different lines. This is the case of the G345 that contains almost all the methanol maser of class 2 that have been observed so far. Note that there are two maser lines at 85 and 87 gigahertz that could be observed with the present observational setup of the global millimeter array and have typical flash density of a few Jansky. The stronger millimeter methanol maser is that at 107 gigahertz with flashes up to 100 Jansky. The maser excitation model are able to reproduce the simultaneous maser emission in different lines as observed. These are a plot taken from Krag et al. That show the brightness temperature of 4 different methanol maser lines depending on different gas parameter. As a general result, you can see the 6 and 12 gigahertz maser are always found to be the strongest one and excited under a large interval of parameter range. And the other high frequency maser are excited under more restricted physical conditions. So that allows us, once this model are tuned, to use the lane ratio between different maser lines to accurately constrain the physical condition of the gas. Of course, that relies on a basic assumption of this model that all these maser lines are emerging from the same volume of gas. And that should be actually verified by registering different frequency maser image with milliarsec accuracy. And that, as we have discussed previously, is not a trivial task. We have done this work, for instance, for the strongest methanol maser, 6 and 12 gigahertz, in W3H, verifying that the different maser spots are aligned with an accuracy of milliarsec. Also, for water maser, they are observed many over the frequency range from 22 to 660 gigahertz, and also, as found for methanol, sources are multi-maser emitters. The strongest one, the strongest millimeter water maser are those 183 and 325 gigahertz with flashes of up to hundreds of Jansky. And as found for the methanol maser, the water maser models are able to reproduce the simultaneous maser emission in different lines, and again, the higher frequency mesin line are found to be exactly under more restricted condition of the strongest 22 gigahertz maser. And we could use the line ratio of different mesin line emitted by the same source to constrain the physical parameter on which they depend. Next, I would like to show few highlights of the recent interferometric observation of millimeter water maser. These are sub-millimeter observation of using the sub-millimeter array of the 3 to 5 gigahertz water maser in the nearest high-mass young stellar object, source I in the Orion KL region. The distribution of the 3 to 5 gigahertz maser is given with colored symbol here, and is found to be almost co-spatial with the distribution of the 22 gigahertz water maser that are represented with gray square here. So both are elongated along the northeast-southwest direction. Maybe the 3 to 5 gigahertz water maser are found to be a bit more collimated than the 22 gigahertz. And we know from previous observations that the 22 gigahertz maser are co-spatial with the SCIO ground state maser, whose proper motion has been measured with multi-epoch VLA observation, and giving the information that the SCIO ground state maser are traced in a collimated bipolar flow emitted by source A at a typical velocity of 20 kilometers per second with radii from 100 to 1000 IU from the source I at the center of the flow. So it's very likely the 3 to 5 gigahertz water maser are sharing the same kinematic and physical condition of these other maser types that are tracing the kinematics of this flow. Just at the center of the flow, recent ALMA observation of two high-energy water maser, 321 and 336, have provided the distribution. They emerge at separation of few tenths of arsec from the young stellar object. And while the 321 gigahertz have a first moment and integrated intensity map that are elongated along their flow direction, the 36 gigahertz maser are show a compact a feature. And the velocity centroid map confirm that the 321 gigahertz maser have a distribution elongated along the flow direction here, and the spatio-kinematic distribution is similar to that of the vibrational stated CO maser that has been also observed in this source, whose proper motion have clarified that they are tracing disk wind emerging from source I. On the contrary, the 336 gigahertz water maser have a spatial distribution perpendicular to that of the flow axis, and just are following these gray crosses here, are following just in between of the SCIO maser of the disk wind traced by the SCIO maser. And they're just co-spatial with the 7 millimeter continuum in this region that is best interpreted in terms of an ionized disk. Author propose that these 336 gigahertz are emerging in a ring of warm gas orbiting around Sursai. Probably with temperature of 3000 K, they could be already thermalized, so it's not certain if they are maser or just thermal lines. So it would be certainly important to have information only on the proper motion of these maser structures that are so close to the young stellar object and to derive so the three-dimensional velocity. And so what I've done is to do a simple exercise to calculate the accuracy in proper motion measurement using the AVN 3 millimeter with a baseline of of 2000 kilometers. With a decent signal to noise ratio of the maser line, we can have accuracy in relative position of 0.03 milliarsec. That translates for a source at 5 kiloparsec with only 1 year time baseline in inaccuracy in proper motion measurement of 1 kilometer per second. That is already an excellent value, and that would be a good gain respect with the time baseline of several many years that are presently are required to derive the proper motion with this accuracy of the slow-moving methanol maser. I would like to finally conclude by considering what could be done presently with the VLBI at 3 millimeter. As I have discussed before, the only a methanol for star formation reason to study gas close to the forming star, there is this transition of class 2 methanol maser at 85 and 7 gigahertz that is falling in the range of observable frequency of the global VLBI millimeter array. Typical flashes of the several Jansky. This is taken from the web page of the global VLBI millimeter array, and it shows that with 20 seconds of integration time, the continuum sensitivity with 500 megahertz is at 7 sigma 100 millijansky. If you want to resolve the narrow maser line, we should use a very narrow bandwidth of a fraction of kilometer per second, which translates this figure, unfortunately, in a high value of about 9 Jansky. That is probably is not enough to study this maser emission. So we should decrease this number by several large factors to start the observation of this maser. And considering the basic formula of the baseline sensitivity, I think that we cannot act so much on the system equivalent flux density that are basically dominated by the tropospherical noise or antenna surface accuracy, as discussed previously in other talk. The delta N is fixed by the requirement of observational requirement. Large bandwidth do not help for a spectral line. So the only chance is to increase the integration time from several tenths of seconds to hours. In this respect, I think that the source frequency phase referencing technique can be really a good solution to for a spectral line millimeter VLBI. Thank you very much.
Thank you. Question, comment? Okay, I have one comment. The frequency range of KBN can cover this from 86 to 87 gigahertz. So that will be very good target for KVN.
Good.
Thank you.
I'm happy if I can use the KVN.
Okay.
It looks as if Alma might help here. Is methanol in the science case for beamformed Alma? I was just trying to Google it as you spoke, and I haven't actually found this argument as part of the science case. I think it would be great to write it up.
You already know that is a science case for Alma.
I'm looking at this. I'm looking at the Fish et al. Thing to see whether it's in there. So far, I've only found a reference to fundamental constants, not to the work you're describing here. But if it isn't in there, I think it definitely should be, because it's within the Alma band 3, as you know.
Also, of course, there's a lot of work being done very, very, very recently to improve the knowledge of the fundamental constants of methanol in the lab, as well, which means that I think at the time when the case was written, the Zeeman coefficients and things were basically pure guesswork, but now they're well known.
Yeah, no, see, that is certainly important for circular polarization. Of course, for linear polarization is not a problem. You have the geometry at least on the plane of the sky of the magnetic field. From circular polarization, you need to know that coefficient, the lambda factor, in order to have an idea how to convert the delta V, the Zeeman effect, from the value in the value of the magnetic field. But that is another give another chance to have also a three-dimensional distribution of magnetic field in this region. That would be really good. Yeah, I think that there is still a large. They are working, improving the figure, but there is still quite uncertain value. Not maybe 1 order of magnitude as it was a few years ago, but still.
Hi, Luca. I think it's maybe not looking that bad. Of course, the source frequency phase referencing is certainly the best, but as a compromise, I think if you would allow to integrate a little bit larger, that means get rid of the spectral resolution and do some Henning smoothing. And if you in parallel also adopt, let's say, regular phase calibrators, then you can prolong the coherence time to about a couple of minutes, and then you would go down, coming away from 9 Jansky to a lower value. I mean, practically we find that during a VLBI scan, which is at 3 millimeter, typically something like 10 minutes long, when we do the fringe fitting, we still gain SNR even by integrating as long as 10 minutes, although the coherence time is only 10 or 20 seconds. I mean, the SNR does not increase with the square root of integration time any longer beyond about a minute, but it goes up with the 1/5 or the 1/4 power of the integration time. But it basically means fringe fitting over a couple of minutes is possible, and if one would include ALMA, of course, or GBT in this kind of experiments, I think you can do already something like right now. I mean, it will take a long time to establish frequency switching, and maybe you can do something before.
Yeah, I mean, I think that to start observing this kind of measure, we should really increase not by a factor of 2, but more by a factor of 10 that delta. So it's, you know.
But how would you do the astrometry? I mean, even with having this very high strong collecting area, still you do need a technique to measure astrometry, no? Because this is for proper motion.
Yeah, that's really important in order, because you need to also align different measures with a millisecond accuracy for star formation purposes. Even higher, sub-millisecond accuracy, if you want to study the measure effects. No? Because you have really to be sure that different spots are emerging from the same direction within the spot size. That is They can be 1 milliarsec.
Yeah, so I think for this project you
yeah.
need the sensitivity and astrometry
In astronomy,
measurements.
certainly,
Yeah.
are definitively important. Yeah.
Yeah, just a very quick comment. Sorry, but you don't actually win anything if you increase the velocity resolution more than about, I don't know, maybe half a kilometre a second, because the maser lines are so narrow, you actually lose so much flux in dilution that for the maser itself, you don't win, unfortunately.
But, I mean, if you observe the maser line with, I mean, for methanol, you really need 0.2, 0.3 kilometers. Yeah, that is important. No, because also it's the peak intensity, of course, is strictly dependent on the how narrow is the bandwidth. Because of course, you have really to resort to have the strong peak flux. That is.
Okay. Let's thanks to the speaker again.
Yeah.
Okay. Okay, we will have a 1 hour lunch break. Is there any announcement from LOC? No? Okay, then let's resume in 10:02. Okay. Enjoy lunch.